today, thanks for the cooperation and with all the new technology, we were able to have this conference under this extreme condition. Oh, I'm sorry, I need to introduce myself. I'm Alexis Lau with the Hong Kong University of Science and Technology. I'm part of the academic committee of the conference, as well as the department head of the Division of Environment and Sustainability, and also the Institute of Environment. Thanks for joining the conference. We will have hopefully, if we can have the meeting tomorrow physically, we will have a official welcoming session also. And I hope everyone still keep going to the conference website, because we plan to, if there's any update on the information, we will disseminate that through the conference website.
Wei, maybe you go ahead to share your PPT. I think just we are just about to start at 2 o'clock.
Yeah, maybe can I just quickly introduce the session before? No problems. I think Alexis wanted to hand it over to me anyway, I guess. I didn't understand him either. So also very warm welcome from my side. I'm Andreas Prein. I'm also on the scientific organizing committee of this workshop, and I'm at ETH Zurich and leading a group in high resolution modeling there. So because of the circumstances that we are in today, we decided to move ahead with the schedule as it was at the beginning at this time. So we first start now with the kilometer resolution modeling for extreme event 3 session. And our first speaker will be Wong from the Hong Kong Observatory. Thank you very much for taking time. Today, I can imagine it's quite busy for you, and he will talk about AI-assisted numerical weather prediction at the South China successes and challenges in their field.
Okay, thank you, Andrea. Can you see my screen about the presentation? Full screen mode?
Looks good, yes.
Thank you. So thank you for inviting us to give this first talk of the conference. And luckily, due to very extreme rainfall today, we have to move to online. And I'm Wong from Hong Kong Observatory. And actually, this presentation should be delivered by our assistant director, Mr. Cheong, but he's so busy now. So I will do for him on his behalf, and presenting our recent work about using kilometer-scale AI assistant modeling for South China. We give you some cases of showing very good result and highlight some challenges ahead. Okay, so I think everyone here is very familiar about the rapid evolvement of the AI technology in recent years. That quite a number of IT giant and the tech expert is developing this kind of the AI weather model, or specifically we name it as an AI data-driven model. So these are from NVIDIA, Huawei, Google DeepMind, and recently Microsoft, showing very promising performance in capturing or forecasting medium-range weather. And actually, we also run a couple of models in HKO since mid-2023 to do the weather forecasting as a kind of internal trial. And various AI models, real-time forecasts, are also made available on our HKO website. If you go to our website, click into Earth weather webpage, that you can see the GIS-based website that you can find the model forecast from several AI data-driven models. These AI-driven data-driven models are very competitive with, or even better than, the traditional physics-based NWP models for some aspect, especially after a lot of literature researching on its performance, that it can capture quite well about the synodic scale evolution that makes quite a very good advantages in tropical cyclone track forecasting. But of course, due to the resolution and also the training data set, basically based on the ERA5 data, there are some essential variables that are not really very well captured, especially for forecasting heavy precipitation and tropical cyclone intensity. So yeah, been quite a very popular research topics that, especially for operational forecasting, that how we can combine the advantages of AI global models with the high resolution conventional NWP. So that's a quite the first attempt. Maybe other community has also been looking at this issue, is to try to drive a very high resolution regional NWP model using the boundary conditions and initial conditions from the AI data-driven global models. So in HKO, we introduced this kind of atmosphere ocean wave couple model system from the University of Washington, so-called the UWIN-CM, for operational trial with a focus to improve tropical cyclone forecasting, especially in the intensity part. So the idea is simple, that we use the UWIN-CM with the initial and boundary conditions from the AI data-driven models, and then try to improve the skill in capturing some fine-scale structures or details. So UWIN-CM consists of the three components. The atmospheric part is the WRF ARW, and the ocean part is the HYCOM, wave model is the UMWM, and the coupler is the Earth System Modeling Framework. So without going into details, I show you here about some of the result that we use the UWIN-CM system in performing the forecast for several impacting Hong Kong that we necessitate the insurance of tropical cyclone warning in 2024, that we used three global models, the Pangu weather, the ECMWF AIFS, and the physics-based IFS as the initial natural boundary conditions of war in the UWIN-CM. So you can see from the left side of the left panel figure, it shows you the mean direct position error, that basically the original ECMWF IFS and the IFS-driven UWIN-CM has a growing error towards the day 4, while the AIFS and also AIFS-driven UWIN-CM together with the Pangu and Pangu-driven UWIN-CM has improved quite a lot, maintaining the error within around 120 something kilometers out to the day 4 forecast. More interestingly about regarding the maximum wind forecast of the tropical cyclones for these 7 TC cases, that we use the IFS and the Pangu global model as a baseline, and the IFS also capturing a little bit larger error, although it's better than the AIFS and Pangu due to the high resolution in the physics-based IFS with the 10 kilometer resolution. So driving the using the IFS to drive the UWIN-CM, we also see some improvement in short term, and then the error gradually grow to day 4. But with the AIFS and Pangu data-driven UWIN-CM, we see the error in terms of the mean absolute error on the maximum wind still maintaining quite a good level, maintaining around below 15 knots out to the day 4s ahead. So you can see a very remarkably improvement in the intensity forecast by using the AI data-driven models as an initial boundary condition to drive this kind of the couple model, getting the high resolution features and a more skillful intensity forecast out to day 4s ahead. So another case is on the using this kind of concept into forecasting the rapid intensification, and we pick a case in using the super typhoon Yagi happening in September last year. That you can see on the left panel, the star represent the red star represent the actual analysis intensity, where you can see the Pangu-driven UWIN-CM as a similar capturing quite a very good trend in the intensity. Although the UWIN-CM shows some error in the initial stage, but actually the rapid intensification in terms of various initial model time, that the trend is captured quite well by running the UWIN-CM driven by the Pangu global AI model. So in terms of the wind structures, we also look into the analysis compared with the satellite data. This is the SAR data that we found that basically the Pangu-driven UNCM got a very good correlation, although still some bias in that. But compared with IFS-driven UNCM, you see a quite remarkably improvement using the AI data-driven model to drive this kind of the couple model to improve the intensity forecast. Okay, next we change a bit in the topics that we use a similar approach. But now we use the AI data-driven model to drive the high-resolution regional ensemble that it hopes to better quantify the uncertainty and to provide a probabilistic forecast high-resolution regional ensemble prediction system with the data assimilation using ensemble common filter being run experimentally in HKO. So this is a 30-member with one control system. When we also use the initial conditions and boundary conditions from the AI global model Pangu weather, taking advantages of the skillful performance in the synoptic scale forecast. And in this ensemble common filter system, we use the all sky satellite data radiance simulation to spin up the model's initial conditions. So here shows you a case study of an active southwesterly air stream bringing heavy precipitation to coast of South China on 7th of June 2025 this year. That this is initialized at 0 UTC on the day before. So we see on the right panel, this shows you the actual rainfall analysis over Hong Kong and Peripheral Delta. And on the left-hand side, this is showing you the 30-member ensemble forecast from the ensemble carbon filter setup that can capture quite a very good the distribution of more intense rainfall basically over rest of the Peripheral Delta and some high rainfall around our area, although the 30-member ensemble may not be sufficient enough to get all the uncertainty, but the general distribution of the more intense rainfall is quite well represented in the model system, especially if you compare to the other global model and limited NWP model on the right, then you can see this ensemble carbon filter system have a quite a very skillful forecast in for improving the weather forecast for the next day.
You have 2 more minutes.
And thank you. So next, we apply this idea into the historical record-breaking Black Rainstorm back to 2023, in which the global model and the regional model may not be really very sufficiently capture the extreme rainfall on the day of on 7th to 8th September 2023. And where we see using this ensemble carbon filter system with the AI data-driven model as the initial boundary condition, better to capture the maximum rainfall over Hong Kong by looking at the grid maps around Hong Kong grid that you can see more than 350 or even more than 550 millimeters of rainfall can be forecast in the day ahead. So finally, this is a summary that in this talk, we basically outlined that the data-driven model in the past couple of years has demonstrated enormous potential on improving operational weather forecast and showing us a very good result. But hopefully that it can enhance our capacity in forecasting extreme weather like what we happened over the past few days. And the hybrid approach using the AI data-driven model driving the high-resolution physics-based region model may be a good approach to tackle a lot of the difficulties like the TC intensity forecast, rapid intensification, as well as capturing the very extreme rainfall by using the more advanced ensemble common filter regional ensemble. So starting from 2025, HKO is making reference to real-time forecast output from all these several AI data-driven models, as well as the high-resolution AI-based, AI-assistant regional models. And we also will continue to leverage rapid progress in the data-driven model ensembles, as well as more further technique development or the applications of AI model ensemble, including the post-processing method, will be pursued. So that concludes my presentations. Thank you very much, and see if you have questions.
Yeah, thank you very much. We have a question in the chat by Yusu. She was asking if you're running a coupled or a forced sea surface temperature forecast with your system.
I'm not sure whether I correctly answered this because my colleague is also online for doing all these things. But we in a couple of model system, I think the SST is capacity kind of the evolving with the input data. That's we will not basically put it as a prognostic variables inside the coupling system.
Okay, thank you. Then another question was about if you have any insights why the AI system improves the forecasts over the physical systems.
Yeah, that's a very good question. Actually, I think this kind of interpretability problem issue is still the some outstanding things that we have to look into. More or less, we got a more deeper understanding that the AI data-driven global models quite good smooth out all those kind of noises, maybe capturing the large-scale flow more skillfully than the physics-based global model. But in terms of the regional model, especially why the inputs of the global AI model with the larger scale forcing into the regional high-resolution model can even improve the forecast, maybe because of the dynamics is better fit into the regional model. Thus, the dynamic factor may help the regional model to capture the basic environmental field with the good forcing to trigger the flow from a large scale cascade downwards into higher resolution. Thank you.
Then another question was if you use spectral nudging or not.
Sorry, I can't get.
Are you using spectral nudging in your forecast? Do you also nudge to the machine learning forecast model?
I think the setup is pretty much straightforward. It's just like using a physics-based global model to drive the regional model, like what everyone here using the WRF by using NSAP or ECNWF to drive the models. We just changed the input to AI global data-driven models.
Okay. So there are a couple of additional questions in the chat. If you could take a look at those and answer them afterwards or during the session, this would be fantastic. Or after, maybe, I don't know if you can join the workshop tomorrow, but people can also reach out to you afterwards. We are running out of time, so we have to move on. Thank you very much.
Thank you very much, Andreas. Thank you.
So the next talk is a keynote talk by Jimmy Fung, and he will talk about high-resolution mesoscale modeling of extreme climate events.
Okay, so thank you very much. My name is Jimmy Fung. So I have this is basically a collection of work by the Division of Environment and Sustainability in HKUST. So I have a bunch of co-author here. I will not go through each one of them, but it certainly is a collective effort. Now, back in 2023 was everyone know that was the hottest year on record, and back then we were hoping 2023 was kept hottest year for a few years, but unfortunately in 2024 yet again break another record. It was the world warmest year again. We are not quite sure in 2025, but however, back in July this year, Hong Kong also recorded the hottest temperature since the record began. I think this is the temperature in Kings Park. It was the hottest record since the record began in 1884. Now, in fact, this is what the hottest temperature in Hong Kong. Actually, the hottest temperature at that day was 37.5. Now, this is the spatial map of the distribution of temperature. Now, Hong Kong, although it's relatively small region, it's just about 1,000 kilometers in area. But however, if you look at the territory, the temperature distribution is quite non-uniform. One of the reasons for that is Hong Kong's land use is highly heterogeneous, as well as a lot of mountain and so on and so forth. So that's why the distribution of temperature. So now in order to understand the heat stress, so we definitely need to have a finer resolution model to capture all these temperature gradients. Now, not only temperature. Now, this is the rainfall pattern we are experiencing today. So this is the record today, and HAO just issued the black warning, landslide warning, thunderstorm, as well as flooding warning this morning. Okay, so this is the radar picture as saw, and this is the rainfall for the last. I think this is the rainfall for the last 7 hours. So you can see the accumulated rainfall can be as high as about 300 millimeter. I think it's breaking the record. It caused a lot of flooding actually in our nearby area in TKO. A lot of the rescue workers going out, as well as causing a bit of landslide. Now, in order to understand a little bit about this, okay, in the future climate, what is going to be all this extreme event is going to getting worse, and how worse can it get? So the way, of course, what we are doing is doing a dynamical downscaling. So the way we are doing it is relatively standard, depending on what pathway we are taking this SFP, and then we using the CMAX 6 to drive our regional model downscaling, using the WRF model hour by hour, and doing about 80 years of simulation down to 1 kilometer resolution. So now this is the resolution picture. You can see typically the global model, the resolution is about 1 degree, so it's about 100 kilometer resolution. If you zooming down into GBA, you can see there's only a few grid, so you cannot see any temperature gradient within the Hong Kong domain. However, if you downscale into 1 kilometer resolution, you can see the temperature distribution has a lot of differences between the global model. So that's the sort of thing we are doing hour by hour based on the CMAX 6 model. So as I pointed out, the way we are doing it using the WRF model, okay, the largest domain cover is the whole entire China with 27 kilometer resolution, with 4 domains slowly zooming down into this smaller region, the GBA domain. So we are somewhere around here, Clearwater Bay. Okay, that's where we are. So now, in order to do the climate simulation, as I pointed out, the Hong Kong land use is heterogeneous. They have urban, they have land use, they have a little bit of forest. So now, as we moving into the mid of the century, so we are also projecting, okay, what is the land use changes as well. So we make a little bit modification on the land use in the mid-century, as well as because of the urbanization, the roughness length of the surface also changes, as well as the albedo, because the urbanization, the different building structure. So all this is built in within our regional model. So as I pointed out, we're doing a few scenarios, okay, 2.6, 4.5, and 8.5. So today I'm mainly talking about this SSP 4.5. So with this simulation domain, of course, we can, as I pointed out, you can get the mean temperature differences on different scenario, as well as precipitation at different at now, mid-century, end of the century, which I will go through a little bit more detail later. Now this is the precipitation PDF we are actually getting. The distribution of rainfall. This is a lot of people want to know how worse can it get as far as the precipitation is concerned. Now the blue one is the current probability distribution in around 2010 to 2020. So this is the distribution. Our maximum rainfall at currently about 150. That's what we are happening today. Okay, so as we are marching on, which is shown by the brown color, so you can see 2050, 2070, 2080, 2090. So you can see the probability distribution, as you expected, is continued shift to the right. Okay, so the the rainfall can be as high as going about close to about 290. So this is scenario 4.5, this is scenario 8.5. So 8.5, you can see, depending what pathway, certainly the precipitation will be worse than what it is now. So based on our climate projection model, so that is the past record on the x-axis is from 188 all the way along to the end of this century. So the blue one is the historical record. So certainly we are keep breaking record up to somewhere we are here now, 150. Okay, our current model also actually capture this type of precipitation in terms of the hourly precipitation. So our model also predict by the middle of this century, the precipitation, hourly precipitation can be 233. By the end of the century, can be high as 300. Okay, that's very serious. So that's why we are working with the government to see, you know, whether they are need to updating their building code, their drinkage, and so on and so forth. If you're looking at the current record, that's what we actually keep breaking the record. It's current 158. That's the Hong Kong record. Back in, I don't know what about today now, whether we are able to break the record, which was 2 years ago. And the highest precipitation record as record currently is 300, around somewhere in the desert in United States. Now, the other thing we want to looking at, of course, is the heat stress. Okay, the extreme temperature, heat wave. How would in this part of the world, how would the heat wave changes? Now, to classify heat wave, the way we are doing it is the heat wave is defined as prolonged period of high temperature, typically lasts for about 3 days. Now, depending how you define it, you can define it as a relative value depending on your temperature is higher than certain percentile threshold, 90% of the climatological value, or you can define it as an absolute temperature. Like in Hong Kong, 33 degrees Celsius as defined as extreme hot day. In China is 35 degrees. Now, the way we are looking at it in this part of the Hong Kong, because we are in the tropics. So when we're feeling the heat stress, it's not just the ambient temperature, because we have a high relative humidity. So of course, humidity actually coming into play. So instead of looking at heat stress, only looking at the ambient temperature, we also taking humidity into account. So there's a parameter called heat index. Basically, it's taking the humidity value into account depending on the relative humidity. The heat stress you are feeling is certainly a little bit more severe. So this is the plot demonstrated on the x-axis is the ambient temperature. On the y-axis, this is the heat index. Yet again, in terms of Celsius, taking the relative humidity into account. So as you can see, as the relative humidity increases from 50 degrees to about 100 degrees, so the nonlinear effect come into play. So you feel much hotter. So when you are relatively high humidity, when the ambient temperature is about 30, in fact, your heat stress is about 40 degrees. Okay, so that's the sort of thing we want to classify rather than just using the ambient temperature. So the heat stress also have looking at sending out warning. So depending on heat stress temperature, so you can see, you know, when they reach about 40 is extreme. So you can send out various warning to the general public. Now, as I pointed out, in order to define the heat wave, you can either do it by absolute criteria or by relativity criteria on certain higher than certain climatological value. So the way we doing it is we using a factor called excess heat factor, which is taking the long-term temperature anomaly plus the short-term temperature anomaly both into account. So the way to doing it is published by this particular paper back in 2025. So this is looking at the last 3 days mean temperature minus your climatological temperature. The high temperature, 75 percentile. If it is positive, it defined as heat stress. the short-term heat stress is yet again looking at the last 3 days versus the last 30 days. And if this particular factor is positive, so this so-called excess heat factor is a quadratic effect of this heat stress, both taking long-term and short-term into account. Now, in terms, as I pointed out, so you want to actually looking at it as we marching on to later on the century, how would be the heat stress actually affecting us? As I pointed out, the heat stress, you can either measure it by the ambient temperature or by the heat stress temperature. So depending how you classify it. So sometimes because the relative humidity is not very high, you can only feel the heat stress by the T2 temperature. If the relatively humidity is relatively high, so you might feeling the heat stress a little bit earlier. You might have a combined effect, both the relative humidity and high temperature. We call this hybrid event. So now, if you look at our regional model doing by hour and hour simulation, afterwards we doing sort of 10-year mean. So this is the current situation of the T2 temperature over the entire GBA domain. So you can see currently in Hong Kong, that's where we are. Our actually mean temperature is actually not too bad. So our mean temperature over the summer is about 26, 28 degrees, not particularly hot. If you are near the Clearwater Bay, where you are, actually our temperature relatively cool compared with the inner part of China. So their mean temperature is about 30 degrees. So now as you're marching further on, you can see the T2 temperature is actually keep increasing. So if you look at the maximum daily temperature is actually increased by the end of the century, actually increased by about 2 degrees as you expected. The global temperature is also similar to this amount. So if you look at the daily mean, it's similar situation and daily minimum. The daily minimum actually increased a little bit more than the daily maximum. As you expect, the minimum temperature actually increased more than the maximum temperature. Now, but however, if you're looking at the heat stress temperature, so you can see the increase is a lot more, okay? Because when you're taking into relatively humidity into account, so you actually feeling the heat a lot more than only the T2 temperature. So as you can see, if you are taking the relatively the heat humidity around, so by the end of the century, the heat stress temperature is actually increased by about 5 or 6 degrees. That also applies to the daily mean as well as the daily mean as well as the daily minimum. Now, if you look at this is just the domain average of the daily max. So if you look at the temperature difference between the domain average over all the land grids between 2040 to 2010, the T2 temperature is only increased by less than 2 degrees. But however, if you look at the taking relative humidity into account, okay, the temperature actually increased a lot more. So increased about 4 degrees. So the minimum increased a lot more. So that you can see. So in this part of the region, because the weather tropic, relatively humidity relatively high. So by the end of the century, so heat stress, heat wave will affecting this region a lot more than drier region. Now, also, if you look at the probability distribution about, okay, how is the daily maximum shifting and the daily mean shifting as you expected, is all shifting to the right. Now, this is the T2 temperature. This is the heat stress temperature. If you look at the PDF, the actually shift a lot further to the right. Okay, so if you look at the extreme value now on the current situation, by the end of the century, it just happened all the time. Okay. Now this one is also very interesting. The way we're looking at domain average of the whole entire GBA domain. The way we are looking at this map now, on the x-axis is the month of the year. This is the day of the month on the y-axis. Okay, so we're looking at 10 years, every 10 years. So on the y-axis, the color represents 0 to 1. So 0, that means no day would be a heat wave. And if it is 1, that means the entire 10 year on this day, 10 day have heat strength. So if you look at it, this is the current situation. Most of the heat wave day happened to around in July and early part of August. Okay, that's where we are. Now this blue circle tell you within GBA the area actually covered to have heat wave. Okay, so for example, if your birthday is actually in July 17th, you are lucky. Okay, for the last 10 years, heat wave doesn't happen. Now, if your birthday is on July 3rd, oh man, you have a hot birthday for the last 10 years. Okay, so now you want to project, okay, what happened in the next mid-century and at the end of the century. Okay, as you can see, by the mid-century, the entire whole July and August would have heat wave virtually every day of the year, okay, in July. And then if you're marching on into at the end of the century, even in September and early part of May. Oh, okay, so that means the heat stress length actually expands a lot more, okay, in terms of the total number of days actually happening. So that's the type of thing which it will be concerned, especially for some of those vulnerable groups. Okay, so this is just the compound effect. I better moving on here. We're also looking at the duration of the heat wave. The heat wave, during heat wave, the maximum temperature. We're also looking at the during the maximum temperature, what is the relative humidity? Also, as you're marching on during heat wave, as you expected, the relative humidity is also increasing as well. Now, the other thing we want to look at is a storm surge. Okay, so this is Wei can talk about a lot. Talk about Hong Kong is affected by typhoon quite a lot. In fact, a couple of weeks ago we have signal number 10, which can cause a lot of damage to Hong Kong, also causing a bit of storm surge. Okay, so one of the things we want to looking at, okay, projected, okay, as the temperature continue to rise, the sea level temperature continue to rise in this part of the region, okay, where the typhoon will be able to pick up more energy. So how stronger can the typhoon can get? Okay, so that we can be to look at the worst possible scenario, what happened around the Hong Kong territory in terms of storm surge. Now, the way we are doing it, yet again, is we are doing the couple model with ocean. Okay, the way we're doing it is the atmospheric model doing WRF, and then ocean model using RAM, the waveform using SWAT. Okay. Now, the way we're doing it is, yet again, this is the couple domain. This is the atmospheric domain. This is the ocean domain. And then we taking all these very detailed terrain into account, as well as the ocean bed. And so the way we're doing it, the first thing, of course, we want to actually validate our couple model, whether it is able to reproduce the situation. The other way is to project, okay, when the sea level temperature increase by the end of the century, about 3 or 4 degrees, how much more energy can this similar typhoon hitting Hong Kong? And then how would that increase in terms of energy? Now, the other thing we want to look at is possible track of hitting Hong Kong, because depending on the track position, which angle, which path hitting Hong Kong, it will have causing different part of the territory to have different storm surge, and then also the sea level rise. So the way we are doing it, actually, we are looking at the historical signal number 10 typhoon for the last 100 years. And then we actually looking at each individual one of them, looking at the pathway and their angle of attack. And then identify, okay, the one probably the worst possible track is actually the one happened a few years ago, typhoon called Mangkhut, caused Hong Kong a lot of damage, signal number 10, and as well as different angle of attack. So we identify this particular path. We do the worst simulation. The other way we are doing it is typically most of the Hong Kong typhoon is formed in south of Philippines, and then they form here, and then moving westward, and then hitting this northern part of the Philippines, and slow down a little bit because it's hitting the mountain region. And then now, but however, if this typhoon will not hitting this mountain, instead of passing through this Luzon Strait, that means low slowdown. So the intensity of the typhoon will remain 250 kilometers an hour before entering the South China Sea, and then continue pick up energy to hitting Hong Kong. That's possibly the worst scenario we will get in Hong Kong if we missing this landing in the Luzon landing. Okay, so
Jimmy, you have 3 more minutes.
So we are assuming we doing this particular worst scenario. Okay, there's a low slowdown of typhoon all the way long. At the end, picking up energy all the way long, hitting Hong Kong. Okay, so this is the various location where they have tidal gauge, and we compare them, looking at the wave and so on. So this is the case. This is the simulation of this case. Anyway, the movie is not moving. And we're looking at the storm, the wave height, as well as the storm surge values. And then now we identify a few areas of having some worst possible scenario in Hong Kong. One is this called Tolo Harbor, because of this, basically the water can rushing in here. The other one is Jinbeizhui, where another new development here. Another one is Victoria Harbor. Okay, so we identify this place together with the maximum surge, the astronomical tide coincide with each other, also the sea level temperature rise, and then the possibly the worst possible scenario we're hitting Hong Kong as far as storm surge is concerned, which is hitting about 6 meters to about 7 meters. That will cause a lot of damage to Hong Kong if this type of worst situation the day after tomorrow happens. Now we're also looking at if with this storm surge, what type of damage will actually happen, how many area will be inundated. In Hong Kong, we're using also called the bathtub model, relatively simple model. So we're just looking at which area would actually be flooded around different part of the territory. So this is the typical land use in Hong Kong we got from the land use department with our flood model, and then we can actually estimate it. Okay, this is the land use area. Some of them commercial, some of them residential. So if the storm surge is flooded the grassland, we have no concern. But if it's flooded with some industrial area or commercial building, we have a lot of concern. So these are some of the estimation we are actually looking at during if the worst scenario happen. Actually, okay, a lot will be flooded as you expected. Not much concern, but some of the industrial area, commercial building, about 70% of the industrial site, some of the commercial building would be flooded, because a lot of these science park so happen is built by the side of the coastal area, so they would be a lot of vulnerable. So for example, if they have data center, so on and so forth, they would have need to pay a lot more attention. Okay, so with that, so I will just stop here. So basically, we are using CMAP6 global model, downscale into 1 kilometer resolution into GBA area. By doing that, we will be able to project, okay, what is the future extreme weather event potentially can be, both in terms of precipitation, heat wave as well as storm surge. Okay, and then I stop here. Thank you very much.
Thank you very much, Jimmy. We have a question in the chat, which is, do the future 2-meter temperature and heat index changes reflect the urban expansion effect? This is the first part. And there's a second part. Maybe you can address the first one.
Sorry, I just missed it. Can you repeat the question?
So if the future 2-meter temperature and heat index changes reflect the urban expansion?
Yes.
Like
yeah. So you mean so the urban is certainly have certain impact because if the urban expansion, typically they would warm up a lot more than the grassland. So is the reflectivity is different. The roughness would be different. It certainly slow down the wind, may be able to trap more heat. So that's the type of phenomenon we're able to see due to urbanization. To some extent, the urbanization, in fact, in this part of the world, it actually also changed the land sea breeze effect during daytime. So because the sea breeze is actually help to alleviate some of our temperature as well. So when it changes the pattern, it depends on where you actually urbanizing your area. So it certainly have certain impact.
And the second part of the question is concerning the response time of the WRF model and the ROMS model. So I think it's more about the spin up. How do you accommodate the spin up in the atmosphere and the ocean if you run your simulation, since you're running a coupled model?
I think, well, I didn't do the simulation. I probably answer this one a bit later. I think we do spin up something like about 20 days, 20 or 30 days before we actually start doing the measurement. Yeah.
Okay, and because of time, we have to move on, but there are a couple of other questions. Maybe you can look at them after,
All right.
afterward. Thank you so much, Jim.
Okay, thank you.
So moving on, our next speaker is Ole B. Christensen from the Danish Met Institute, and he will talk about resolution dependence of simulated extreme statistics for Denmark. Take it away, Ole.
Yeah, I hope you can hear me.
Yes.
And now I hope that you can see the presentation. Do you do that?
Looks good, yes.
Great. Yeah, thanks to the organizers for the occasion to talk here and to see convective precipitation firsthand. I would also like to acknowledge Emma Thomason, who was a PhD student, now a PhD, who did a lot of the analysis that I will talk about. And at least in the beginning, most of the plots, they have been prepared by her. So we are going to Denmark. And what we want to do is something simple-minded. We wanted to do sub-kilometer regional simulations with a convection-permitting model. And we took what we had with various domains in various resolutions and tried to see if we could simply analyze the resolution dependence of the precipitation spectra that were simulated over Denmark with these models. So you will see a lot of maps of Denmark, but you should, of course, keep in mind that they're not just done in different resolution, which is what we will be focusing on, but they're also done for different domains. The model we are using is Harmony Climate. Let me wave the flag here. It has been developed from the Harmony weather forecast model, which and the Harmony Climate model is being used by a lot of the kind of smaller countries in Europe who've gone together in a consortium. There is a list here of the members, and there's various sorts of evolution of the model, development of the model going on in all these different countries. We use some French physical parameterizations for the convection-permitting resolutions and the non-hydrostatic simulations. We use the Arome package inserted into the harmony dynamics. When we do causal resolution simulations, we have a different physical parameterization package, the Aladdin package. Our surface description is Surfex, also French, and we work on coupling. I mean, these coupled models containing harmony climate as well as NEMO, they're under development, and we don't have any production simulations yet. Of course, what we want to do is try to look at high resolution. We don't have that many very high mountains in Denmark, but still it is a very heterogeneous place where it does make sense to run models in high resolutions. High resolution. So we have recently been doing a lot of kind of causal resolution things, cortex simulations, and several polar, that is Arctic as well as Antarctic simulations in causal resolution. But we've also been doing a bit of high resolution stuff. So the results I want to present here basically come from two sources. There is a big collaboration effort, which we call NOR-CP. That is the bottom map you can see, where several 20-year time slices were simulated with 12 kilometers in an outer nest and a 3-kilometer, pretty big area here that contains both Norway and Sweden and Finland and Denmark. And we kind of distributed our ECMWF billing units between us, and each institution in each of the countries did a couple of time slices. We have reanalysis-driven simulations, which is what I will talk about here, but we also have EC Earth-driven as well as GFTL-driven climate change simulations. Then what we have here to supplement is a 750-meter resolution simulation just over Denmark, which you can see in the upper right. And the way we did that was that we took Area 5 and put an outer nest in a 5-kilometer, but still using the Arome physical parameterization. And then inside that, we put the 750-meter resolution area. That's expensive, as you all know. So therefore, we couldn't do very long simulations. What we did was that we took the summer half year, basically from April to October, that is 7 months, and we did that for 5 years. And when I compare, or when we compare results here, those are the periods we are looking at. And I can tell you we are not aiming for a climatological average. These years, they were chosen as years where there were observed extreme precipitation events in Denmark. When we validate, we compare to a network of gauges, which you will see in a tiny moment, which you can read about here. So, just in summary, those are the two ways we do it. I shouldn't repeat myself with this tight time schedule. This is the kind of plots we'll start showing. So in the upper right, you will see point-wise observations, station observations, as little circles with colors in them. And then we have increasing resolution as you go down. To the left, you have the area interim simulation, reanalysis driving the 12-kilometer Aladdin harmonic climate simulation. again driving the 3-kilometer simulation in the NorCP experiments. And to the right, you have the more modern, the more recent Era 5 reanalysis and the 5-kilometer and 750-meter simulations. And everything looks great in the beginning when we look at average precipitation. If you kind of eyeball the maps here, you can see that when you go to the very high resolution, you see that this erroneous maximum on the west coast when the ocean meets the land moves inland to what we know to be much more realistic, that most of the precipitation in Denmark will fall over this mountain range, if you will, the highest elevations in Denmark, which go kind of upwards through the backbone of Jutland. Also, when you look at these box plots to the right, you can see that the high resolution simulations, they are much better than the lower resolution simulations. Let's gradually go towards extreme precipitation. First, the wet days. You can see that this infamous drizzling problem that we have always had, I still remember, etc. That is, as you've also seen many times in other simulation sets, it disappears when you go down to the higher resolution and the convection-permitting parameterization. We have much more realistic numbers of wet days. We now go to extremes. We take the 1/3 year return level and look at that. We have that in different durations, 15-minute duration, 30-minute duration, hourly, and 6-hourly. Picked it here. We also have other resolutions, of course. And again, we see this, everything is good in high resolution, but it's worse in coarse resolution. What we are kind of missing is a continual improvement as we increase the resolution all the way to 750 meters, which is a bit thought-provoking. Let's look at the maps, and we see the same as I just showed you. You can see time is running. That we can't really conclude that the 3-kilometer simulation is worse than the 750-meter simulation, but they are definitely seen together much better than the coarser resolution simulations. I'll skip this, I'll skip this. So we tried to focus a bit more. So I did for one of the years, 2017, just one of the years, I did exactly the same very small area as the one where we did the 750 meters, and then I just decreased the resolution by a factor of 2 and another further factor of 2 to see if we could learn anything from doing that. And I'm afraid the answer to that question is no. I did not become much wiser by looking at that.
One more minute.
Yes, average precipitation is fine. This is just removing the sea part and the boundary part. So you see everything is fine, it's in the right place, but you do not have a kind of systematic increase or systematic anything when you look at it as a function of resolution. Looking at the extremes, again, the 750 meter does not have higher extremes than the coarser, artificially coarser resolution ones there. This is the maximum for that year. And of course, you see events. Again, you cannot conclude that we have really gained anything by going to the trouble of making a 750 meter simulation. So, I mean, there is room for improvement. There's more research to be done. But at least in several aspects, as I hoped I could show you in this short time, we improved our results, but the extremes did not kind of develop in a systematic way as this simple function of resolution. Yeah, no time. We are working on the model. The results I showed you here is from a previous version of the model. So if we want to study things further, we'll need to do everything again because we have a more recent model version now. Thank you very much.
Yeah, thank you, Ole. Actually, we have similar results, actually, that the differences are not too big if you go from 3 to 1 kilometers in extreme precipitation. But like, there's a question in the chat concerning that. Would you say that 3 kilometers is a sweet spot then for modeling extreme rainfall over Denmark?
I mean, I would not say that this analysis is in any way complete. I mean, there are several loose ends. I mean, if we look at the results I showed in isolation, yes, I guess we can conclude that we didn't gain anything going from 3 kilometers to 750 meters, which is, I mean, that's a factor of 4 by 4 by 4, right? It's much more heavy to do the 750 meter simulation, of course. But I mean, I would not stress that conclusion. That is what it looks like currently, but we need to do more simulations.
And we have another question concerning where the benefit comes from if you go from 12 to 5 kilometer or higher resolution. Like, why do you think?
Well, 12. You saw the 12 kilometer simulation with parameterized convection and hydrostatic dynamics was considerably worse when you looked at both average and extreme precipitation. And of course, I know Denmark is small. It is when you look at areas of this size, obviously you gain more by going to higher resolution. I know I'm not telling you anything new here.
But it's the convective dynamics, not the topography. That's the main point, isn't it? Like,
yeah. I mean, yes, of course, I have not really separated those two effects when I did the simulation, but yes, I believe you're right.
Okay, that also, I think there's one more question for you in the chat. If you could take a look at this, we have to move on because of time. Thanks,
yes.
Ole.
Thank you.
Next, we will share. Lizzie is online, but she recorded her talk, so we will share the recording, and then Lizzie, you could answer the questions if there are any afterwards. So Lizzie will talk about tropical cyclones in South Africa.
Hello, my name's Professor Lizzie Kendon. I'm Head of Climate Projections at the UK Met Office and Professor of Climate Science at Bristol University. So I'm going to be talking about new insights into changes in tropical cyclones over southern Africa using kilometer-scale climate projections. This is work under the Reale project, which is all about trying to improve resilience and preparedness to tropical cyclones over southern Africa. It is a project that's funded through the UK International Development and also IDRC in Canada, and is as part of the CLARE initiative. So I would like to thank all of the Reale team who've contributed to this talk. Now, Tropical Cyclone Idai struck in March 2019 and was the first cyclone to ever lead to more than 1,000 deaths in the region. And in fact, 600 people alone died in Beira on the Mozambique coast due to the storm surge and flooding. Now, in the future, we expect tropical cyclones to get more intense under climate change, but actually how they make change in this region is uncertain. Now, within the Reale project, we are exploiting the first multi-model ensemble of kilometer-scale climate projections for Africa. So these consist of a set of Pan-Africa simulations at 4.5 kilometer resolution that we've run at the UK Met Office. They also consist of an ensemble of simulations run by CCAM at the WITS in South Africa. And this is a stretched grid model which goes down to 4-kilometre resolution over the region of interest. Now, for each of these models, we actually have a 5-member ensemble driven by different CMIP6 models with a 10-year present day and a 10-year future simulation. So this amounts to 50 years of data from each of the different modelling sets, which is an incredible resource and is really allowing us to provide new insights into how tropical cyclones might change in the future. Now, these models really give an improved representation of tropical cyclones, which is what we can see here illustrated by this particular case of tropical cyclone Enawo, which struck in March 2017. The left-hand panel of the animation here is showing the observations. The central panel is showing the CP4A model from the Met Office, and the right-hand one is showing the reanalysis data, ERA 5. Now, the model in the centre is free running, there's no nudging, it just receives information from the reanalysis data at the lateral boundary. And you can see it's able to spin up a tropical cyclone and capture all the spatial structure, part of its internally generated dynamics. And then the tropical cyclone follows the track going down Madagascar and then weakens slowly and goes off further south. And indeed, on the right-hand side here, you can see the time evolution of sea level pressure for this tropical cyclone. The green line is the ERA 5 reanalysis, and you can see this underestimates the intensity of reached by the tropical cyclone. The red line is the observed tropical cyclone, and the blue is the CP4A model. And you can see it's able to capture, in this case, the timing and intensification very well of an intense tropical cyclone like this. This is another example looking at tropical cyclone Freddie, this time in the CCAM model run by WITS. Now, tropical cyclone Freddie was in 2023 and was another tropical cyclone that led to more than 1,500 deaths, and in fact was one of the is still the world's longest tropical cyclone on record. And you can see in this case, CCAM is really nicely able to capture the structure of the tropical cyclone with its double-banded rainfall bands. On the right-hand side, top right here, we have the track of tropical cyclone Freddie as seen in the observations, and then rain gauges coloured by the amount of rainfall that was accumulated. Now, on the bottom panels here, we are plotting rainfall in the CCAM model versus the rain gauge data. And you can see both for Mozambique in red and Malawi in blue, the rainfall totals lie on the 1-to-1 line. So CCAM is really well able to capture the sort of rainfall amounts that were observed in reality as part of tropical cyclone Freddie. Whereas on the right-hand side, which is the rainfall in ERA 5 compared to the rain gauge data, it curves off. And so the highest rainfall totals here of 1,000 millimetres just are not seen in ERA 5. Now, on the left-hand side, we're showing how, over a course of many tropical cyclones, how the relationship between sea level pressure and maximum wind speed is captured. The back line shows this relationship in observations. And now the blue line is this new CP4 run, and you can see it's very well able to capture this relationship, which is really important for giving us confidence that it's capturing the processes correctly within the model. Now, the reanalysis data is actually shown in yellow. You can't see that because it underlines the green line, which is the result for a very high resolution 25-kilometre model. And you can see in this case, it is not able to capture this relationship and certainly does not capture the most intense tropical cyclones that we see in this region. So this is starting to really give us confidence in terms of being able to explore how some of the most intense tropical cyclones might change in the future. What I've plotted here is looking at the track density of tropical cyclones in the region. On the top, we're just showing the historical track density. The first plot shows the tracks for all low pressure systems that reach a tropical cyclone intensity at some point in their track, but it's the full track. So both the genesis, the development, and then the decay. And in this case, for all of these, considering all tropical cyclones, we can see that on the bottom, we expect a decrease in the future. I should say in this case, I am showing the mean results across all 5 ensemble members for all 10 years of the future and all 10 years of the present. So 50 years of data have gone in for each period. Now, if we move on to look at ever increasingly intense tropical cyclones, we see a shift now from an overall decrease to actually increases, certainly in the southern part of the region. And this is consistent with what we basically expect, that we expect tropical cyclones in this region to decrease in frequency, but the intensity to increase, such that for the most intense tropical cyclones, so category 5, that we may expect an increase in this region. Now, this is something we haven't been able to look at before. I should emphasize, typically climate models do not capture category 5 tropical cyclones. So this is the first time we can get insights into how these are changing. So these models are showing us that we really need to be prepared for a category 5 tropical cyclone making landfall over southern Africa. And this would be unprecedented in the historical record. So what we're showing here again is this relationship between pressure and wind speed. The observations again are shown in black, and this time the blue line is the historical data from CP4 and the red line is the future. And you can see how we're shifting into the category 5 regime as we move into the future. So we do absolutely need to be prepared for some of the most intense, devastating tropical cyclones to make landfall. Now, here we've been looking at how rainfall associated with the tropical cyclones might change. This is important because tropical cyclones bring quite a large proportion of the rainfall that falls annually, particularly in Madagascar and some of the coasts of Mozambique. And in the future, we see that the contribution to rainfall from tropical cyclones is decreasing over quite large parts of the region, shown here in brown. Now, the individual ensemble members, which are shown on the right-hand side, do show some different regional differences here. But if we average them all, we can see there's a consistent signal, and certainly over Madagascar, there's evidence in all of them that there is going to be a decrease in rainfall in the future. So this is telling us that not only do we need to be prepared for very intense tropical cyclones striking the region, and which could be very likely lead to serious flash flooding, but also there could be an overall decrease in rainfall. So there's a risk of slow onset impacts, in particular drought. And this is something we're starting to see evidence for already. Another aspect that we can now start to look at for the first time is rates of intensification. So this is how quickly a tropical cyclone develops, and clearly which has real important implications for how much warning time people have to evacuate. Now, on the left-hand side, we're showing the probability of having a tropical cyclone that intensifies rapidly. There's a particular definition here of the rate of intensification within a 24-hour period. And the green bars show the observed probability of this occurring. And the kind of dark red bar, very short dark red bar, is the best performing high-resolution global climate model. And you can see it's significantly underestimating the occurrence of these sort of events. Now, the blue bars are the results for the CP4A ensemble, and you can see that these now are very well able to capture the sort of rates of rapid intensification that we see in reality. And if on the right-hand side now we start to look at how this might change in the future, it is fair to say that not every single model is showing evidence of an increase, but 4 out of the 6 models suggest that there's a 50% or more increase in the likelihood of rapid intensification in the future. So that has real concerns. So not only do we need to be prepared for very intense tropical cyclones, but we may also have less warning time of them making landfall. And this is just a final result that I'd like to share with you. This is looking at what-if scenarios. So here we are running the kilometer-scale model, CP4A, for relatively short periods corresponding to a historical event. But we're running it with slightly different initial starting points just to capture some of the noise in the system. So what-if scenarios, what could have it looked like? Now, on the left-hand side here is the track that IDI actually took. But some of the plots on the right-hand side here are other alternative versions that could have happened under those conditions, just if we have a little bit more noise with a bit of noise in the system. And in some cases, they look very like what was observed. But on the bottom right hand here, we have a very different situation where tropical cyclone Idai could have recurved in the channel and gone on to make landfall in Madagascar, which would have had significant impacts. Now, these what-if simulations are very useful for stress testing, for allowing people to explore the risks of their systems. And what we're currently moving to do now is to run these what-if scenarios, but in a future setting, climate setting. So what could tropical cyclone Idai have looked like in the future? So this is just a summary. Under the Repraiser project, we have been running two sets of multi-model kilometer-scale climate projections. And these models are now for the first time able to capture Category 5 tropical cyclones, so the most intense tropical cyclones, and rates of rapid intensification as we see it in the observations. And this is really a huge leap forward in our ability to assess changes to the most intense tropical cyclones. Models project a future decrease in the frequency, but an increase in the intensity of tropical cyclones, but there is some uncertainty in the localized changes. But importantly, we need to be prepared for Category 5 tropical cyclones making landfall over southern Africa, which is unprecedented in the historical record. It is likely that tropical cyclones play less of a role in annual rainfall totals, but there's an increased risk of heavy rainfall and flooding in some of the most vulnerable communities. And finally, tropical cyclones may also intensify more rapidly in future with less warming time for people to evacuate. And with it, I'll stop there. Thank you very much.
Thank you very much, Lizzie. Lizzie, are you? Oh, you're there. So we have one question already in the chat. Why do you think the tropical cyclone total rainfall is decreasing in the future?
Yeah. I mean, I think as they put in the chat, I think that's right. I think it's basically down to the decrease in frequency. So, the overall rainfall totals within the season are primarily coming from that frequency signal. But I guess one thing we yet to look at, but we very much do need to look at, is the distribution of some of the heavier rainfall totals, because we suspect that will be increasing.
And then another question, I had the same question actually. How do you treat the sea surface temperature? Is this coming from GCMs? Is this coupled or?
Yeah. So the very important caveat, these runs aren't coupled. We're about to try and do some coupled runs over Africa because we're well aware that that is a limitation here. So we are using the SSTs from the driving coupled models, so the CMIP models. So obviously that means that we are not capturing some of the feedback processes. I guess in this case, well, I suppose aspects of the landfall and particularly the interaction with Madagascar, we are hoping is reliably captured, but absolutely risk that the intensity might be overdone because we're missing some of the coupling elements. So that's something we want to try and explore. But we have been doing some analysis of some of the high resolution global models from the ERIE project, which are coupled, so they're 25 kilometers. So they're complementing what we've got here. But the main difficulty we have with those is they just don't capture the most intense tropical cyclones. So they don't really go anything like, well, we don't see anything Category 4 and above in this region in those models. They are capable of producing Cat 4 and above in other basins, but not in the Southwest Indian Ocean. So yeah, but yeah, that is definitely a caveat of this work.
Yeah, it will be interesting to see those results once you start coupling at high resolution.
Yeah.
So because of interest of time, we have to move on. Thank you very much, Lizzie, and let's thank all the speakers in this session 3 one more time. And I hand the mic over to, I think it's Fei Chen, who is hosting the first session.
All right, so we're about to start the session, okay, which is supposed to be the session, okay, in the morning, rescheduled to this afternoon. And hello, everyone. I'm Fei Chen from the Hong Kong University of Science and Technology, and I welcome you all. I'm so happy to see you here. Despite all these crazy events happening today. So this is we are in our session. We had 4 talks today, and the first speaker is Jason Evans, okay, from the University of New South Wales, and he's going to give a keynote speech, and the title is Kilometer-scale modeling for Australian cities and Pacific Islands. Share your screen when you are ready.
Okay, thanks, Fang. So I'm Jason Evans, and I'm based at the University of New South Wales in Sydney, Australia. And in this presentation, I'm going to show you a number of different activities we have happening in Australia using kilometer-scale modelling. So here's what I'm going to cover. I'm going to talk about 2 initiatives, NARCLIM and some work we're doing, but focused on the urban environment first. And then I'm going to describe to you 2 Cordex flagship pilot studies that started just this year. One focused on sub-hourly extreme precipitation, and the other one focused on Pacific Islands and their climates. So first I want to talk to you about NARCLIM, NARCLIM 2.0, which we're up to now. So NARCLIM stands for the New South Wales and Australian Regional Climate Modelling Project. It's led by the New South Wales state government in Australia. So this is the most populous state in Australia. And essentially, I've been working with them for many years, and we've produced regional projections that underpin all the government department climate risk assessments and adaptation plans. And the department, they've created a climate science team, and they've hired in a whole lot of climate scientists. So they've got a lot of in-house expertise now, which they didn't have before. And so they're the ones who really taken control and produced the simulations for this project. And what they've managed to do looks a bit like this. So the domain setup is that they're modeling all of the Cordex Australasia domain at 20 kilometer resolution, and this quite large area at 4 kilometer resolution covering all of Southeast Australia, which includes some 75 or 80% of the population of Australia. Now they've done this downscaling for 3 different emission scenarios, 126, 245, and 370. In every case, it's a continuous simulation from 1950 to 2100. And they've created an ensemble by downscaling 5 different CMIP6 GCMs using 2 different configurations of WRF. So there's effectively a 10-member ensemble, and for 150 years for 3 different ensembles. So this is many, many, many years of modeling that's been done by this team. And you can see a lot of the names of the team on the slide there for that publication that describes the experimental design and the first evaluation part of the project. So let's have a quick look at some of the results we're getting at 4 kilometers compared to what we see at the 20 kilometer resolution domain. Now here we're looking just at the Southeast Australia area, and you can see in the figures here, this is the bias compared to a gridded observation data set, and the white patches are where the observations are sparse, too sparse to have confidence in, so they're just masked out in white. And effectively what you can see here in the numbers in the bottom left of each panel is the area average bias and mean absolute bias. And so you can see a general improvement at 4 kilometers. But what was probably more positive for the team is that you can see that the strongest bias at 20 kilometers is right along the coastal area, along the eastern seaboard of Australia there, as well as a bit further south where we have our highest mountains. But certainly for New South Wales and for Queensland, most of the population lives in this eastern seaboard area. So having the strongest bias in the 20-kilometre model in that area was not ideal. And you can see that at 4 kilometres, we've really done a much, much better job in that area. So capturing the coastline effects and the eastern seaboard is happening much better at 4-kilometre resolution. Now, here we're looking at, that was the mean precipitation. Here we're looking at the 99.9th percentile precipitation, so precipitation extremes. So again, if we focus on the left-hand most panels, you can see the left-hand most one is the gridded observation data set. And then all the other panels are showing you the biases or differences to that observation data set. The top row is the 4-kilometre models, and the bottom row is the 20-kilometre models. You see the multi-model mean bias on the left-hand side, and then on the right you see some example individual models. So if we first just look at the multi-model mean bias, again you see a kind of story that we saw for the mean, and that is that at 20 kilometres we're seeing some of the strongest biases in that eastern seaboard area, and at 4 kilometres the models are able to do a much better job in that eastern seaboard area. If you look at the individual models, of course, you still see a range of results here, with some being generally wetter and some being generally drier. But in almost every case, that eastern seaboard area has lower bias at 4 kilometres compared to the 20-kilometre resolution model. So again, a consistent improvement in this area. Now here we're looking at results for temperature. In this case, it's a 99th percentile minimum temperature, so extreme minimum temperatures. And it's a little bit different to what we saw with precipitation, in that we don't see the largest differences in bias in that coastal eastern seaboard region. But we do see a general improvement or decrease in the bias sort of generally across the area. An improvement of about 15% on average, which was also a nice result. Now, this NARCLIM simulations are relatively new. So this analysis we're seeing here is some of the first analysis that we've done, but with 150 years of 10-member ensemble at 4 kilometres, this is really a wealth of data, and there's lots of analysis that's been started, and over the coming year or so, we should have some really interesting results to be looking at out of this data set. So next up, I want to say a few words about some of the work we're doing looking at the urban environment and its relationship with climate, or feedbacks onto climate. In particular, we have one project that's focused on the changing urban environment of Sydney. Like a lot of big cities, and perhaps Hong Kong's in the same boat, over the last few decades, you've seen quite a big change in the urban environment itself. The city spreading to new areas, the city increasing in densification and height. And so we're really interested in how this evolving urban landscape is also implicated in the changing local climate that the city is experiencing. And for a lot of coastal cities, like Sydney, the water supply catchments are just inland of the city. And so a lot of the rain that ends up being the water supply for the city comes from storms that actually cross the city from the ocean before getting to the reservoir. So changes in the city that are changing the interaction with the atmosphere above, and those storms are also impacting the water supply for the city. So we want to understand better how that's happening. So the first step for this is that we have to understand how the city has been changing. And so we're doing that by applying these local climate zones, identifying the local climate zones in the city, and then going back in time in how they change. So if you haven't used this setup before. The local climate zones give multiple different types of urban landscapes, as you can see in that list in the middle there, with the compact high-rise being the most dense urban landscape with high-rises, all the way through to, you know, sparsely built areas that might be out on the fringe of a city. And the way that we do this is we do a bit of machine learning with a random forest classifier. And you can, I just zoom in a bit here on the city. And so essentially this is, you know, image you can get from Google Earth, and you can use Google Street View, and you can identify areas which are clearly one of these local climate zones. So this red area in the middle here, this is downtown Sydney, and this is compact high rise. It's all, you know, high rise buildings of 20 stories or more in this area. Now that works really well when you're doing it for the recent years, because we can get Google Earth images for the year of interest, and we can look at the Google Street View from recent times as well. But when we want to go back in time, we don't have the Street View anymore. But with the Google Earth images, you can go back in time. And so what we do is that we've gone back every 5 years from 2020, and we re-examine our training areas. So this red outline is one of the training areas, and we check whether or not it is still, all of that training area is still that class. Sometimes a part of the training area isn't that class as you go back in time, and so we change the training area to only include the class, and then we do a reclassification for each of those years. So here's for 2020, this is what the classification looks like. You can see in the hash blue here, the water supply catchment just to the west of the city. Here I can zoom in and you can see the different colors showing the different urban classification land use covers for the city. And then here showing how it works for every 5 years going back to 1990. You can see each of the maps there, and you can see by eye very clearly that they become redder and redder as the city has become essentially more and more dense. And it's densified much more than it's spread since 1990. And then you can see on the right here, this is just showing the normalized number of grid cells in each class. And clearly for our most dense urban classes, these first 5 classes, we see very clear increases in those classes. And that's coming at the expense of some of the open low-rise classes and the sparsely built classes. So previously these fringe parts of the city are being absorbed into the city better. Then we put this into WRF. You know, just the default land cover is just a very dense urban cover that you can see in that top row. And now instead we're putting in this changing urban cover you can see in the bottom row here into our WRF simulation. And then we're running this through time. Here's just some initial results. These simulations are actually still running. We've only done the controls, completed the control simulation at this point. And you can see that WRF is certainly doing a pretty good job in capturing the wet years and the dry years and the general locations of where this rain is falling and so forth. Now, in the last 3 panels here, you might be able to make out a couple of circles. There's a couple of light circles in these first ones here. If you look really hard, you might see there's actually many other circles. These circles are the station data colored with the same color bar as the model. So when you can't see the circle, that's because the model's done such a good job. It's basically identical to the station. And you can see that generally speaking, the stations are quite hard to spot. So the model's doing quite a good job overall. So in this project, we've run this 1990 land cover simulations. We're now running the changing land cover simulations. So this will help us understand how the changing urban environment on its own is affecting that. Then we have a third experiment that we're also putting together where, along with the changing urban environment, we'll also be changing the aerosols and pollution that's being produced over the city as well. And then after this, the final step after this will be to have some future scenarios that include changes in the urban landscape into the future, along with the changing climate. But we're yet to get that work done. Okay, so for the second half of the talk, I'm going to tell you guys about 2 Cortex flagship pilot studies. Both of these studies started at the beginning of this year. So the first one I'm going to talk about is SHEP, the Sub-Hourly Extreme Precipitation Project. So we're learning that these sub-hourly extreme precipitations are changing quite fast. We know from our observations that they're often very small spatially, maybe just a few kilometers across. So they're not really represented at all in lower resolution models. We really need high resolution models to look at them at all. And there's been a whole bunch of publications looking at observations in various ways that are showing increases in these sub-hourly precipitation intensities, often changing faster than longer duration rainfalls. So we're really interested in trying to understand why that is and understand whether our models can really produce those kind of extremes. So here's the aims of SHEP. First, we want to quantify the observed changes in these short duration precipitation extremes over the major Australian cities. Australia is kind of a good example because we've got cities in the tropics all the way down to cities in the southern extratropics. So a good range. We want to then evaluate the ability of the convection permitting climate models to simulate these short duration precipitation extremes. And then to simulate these changes in these extremes due to climate change going forward. There is a SHEP website. If you're interested, you can probably just Google that. And of course, this is it's an open collaborative community effort. If you are interested in joining the effort, please contact me. I'm very happy to get people involved. So the first activity we're doing is an event-based analysis. So first up is to quantify the observed changes. And we're doing this by looking at data from automatic weather stations, from weather radars, from a regional reanalysis. We got some data from the state emergency services telling us about localized flooding and impacts that they have to deal with, damage reports and so forth. So once we've done that analysis, one of the things we're doing is identifying a series of extreme events to simulate with the models at kilometer scales. And then we'll be moving into this first step, which will be a reanalysis driven, really focused on trying to evaluate how well the models can do for these events and improving them if we can, so that they're better able to simulate these events. And then the last step for the event-based analysis is to do a pseudo global warming experiment where we're going to then ask the question, how would these events evolve in a future warmer climate? The next activity is to move on to climate length simulations. And here we're going to go, so this probably won't start before next year sometime. We're selecting some CMIP6 Australasia, Cortex Australasia simulations. We have quite a large Cortex CMIP6 Australasia ensemble at the moment now already, something like 40 members. So we'll start from them, and we want to do some coordinated simulations for the recent, past and future. Now, unlike NARCLIM, we're probably not going to be able to do 150-year continuous simulations for this. So we're looking at doing 20 or 30 time slices in the recent past and into the future. Now, we also have some groups focused on using AI techniques. And there's two real things we're hoping to be able to do with that. One is to expand the convection permitting ensemble, that is to downscale from the other Cortex CMIP6 ensemble members that we won't be doing with the dynamical kilometer scale models. And the other thing we want to try and do is to also fill the gaps between our time slices that we do with our kilometer scale dynamical models, fill the gaps with the AI techniques. And lastly, we're working with stakeholders with this work. It was really motivated to a fair degree by recent work we'd done on the guidelines for engineering design of water sensitive structures. In the process of doing that, it became clear that very little was known about these short duration extreme precipitation events and how they might change with climate change. And that's the gap we're really trying to fill with this work. And we're working with the same group of engineers and consultants that are using that data to design their structures. And here's a quick look at just one result. Here, this is based on station observations for the Greater Sydney region. And you can see at different durations, we're looking at the trend in the intensity at different durations for the 99th percentile. And you can see mostly upward facing triangles. So mostly these things are increasing, but you can also see that the size of the triangle, which is proportional to the size of the trend, tends to be bigger for the shorter durations compared to, say, the hourly duration. So that's the observations themselves are telling us that these extremes are increasing faster at shorter durations. And we've been looking at weather radar observations. And here's an example where we've looked at a day where station observations have said there's some of the 10 most extreme 10-minute duration events that have occurred in the area. And you can see for many of these events, the weather radar indeed agrees that there were some very extreme events on those days. But if you look at the very left-hand side, you can see there's a couple of days where the weather radar doesn't say or doesn't think there's anything substantial happening. But at least one of the automatic weather stations thinks that there was quite an extreme event on that day. So that's an interesting phenomena we'll look into more. Don't know if that was, someone spilt some water on the weather gauge or what happened there. But it is interesting that we have seen that actually at every city we've looked at around Australia. There's some days that come out like that. Okay, so now I'm going to go on to the last one. This is the Pacific Islands flagship pilot study. Now, why do we care about Pacific Islands? Well, Pacific's a very large area. It's bigger than some continental areas. And the islands themselves are quite vulnerable to climate hazards. Everyone's probably heard about sea level rise being an existential threat to some of the low-lying islands. But of course, the islands are vulnerable to lots of other hazards as well, not just sea level rise. Tropical cyclones and heat waves and droughts and all sorts of things. So they need to know about what's happening in terms of all of these hazards to be able to understand their risks and plan for them. Now, the islands most of the islands have coral reefs around them. Coral reefs are a fairly distinct natural ecosystem, really exceptional marine biodiversity. They provide protection for the islands in terms of alleviating the waves and so forth. They're an economic resource because they're a source for fisheries and so forth. And they also have a lot of cultural heritage value. And the corals are very important to the cultures on the islands. And corals are one of the most threatened ecosystems in the world, with already some 20% of the reefs being destroyed. And the islands are not represented in most of the simulations that we are looking at. In terms of, here we're looking at figure showing New Caledonia, which is like the biggest island in the Pacific. And you can see what it looks like in a 100-kilometer model in the top left. It's basically a couple of diagonal touching grid points, nothing like the actual island itself. We need to get down to the kilometer scales before it starts to actually look like the island. So far, and that's the biggest island. The smaller islands aren't present at all in the global model, and it's that oceanic change in climate that is being used to date for most of the islands in the Pacific to estimate how the climate might change. So what we're trying to do in this is to provide climate change projections that reflect the changes to key island climate processes and provide the information that's needed to do climate change risk assessment and adaptation work. Again, it's an open community collaborative project. If you're interested in this at all, again, please contact me. We'd love to have you join in. So our first aim here is to quantify the ability of our kilometer-scale models to simulate the island climates. We're working towards that right now. And then we'll be looking at simulating future island climates and using those simulations to quantify the hazards. Again, there is a website. You can go to that website and have a look at more information. So the preliminary work, here we have our proposed domain setup, where we model the outer area at lower resolution in these green areas over island groups at kilometer scales. So our preliminary work, we're looking at what's been done so far, and we're developing the experimental guidelines for all the groups to follow as they do their simulations. And we've been talking to stakeholders in the regions to understand what are the key climate hazards that they're really concerned about. Then once we've got the experiment protocol together, which hopefully we'll have in the next month or two, then we'll be going ahead and doing the first evaluation experiments. And again, this is really a chance to test the ability of our models to simulate the island climates and an opportunity to try and improve the models where we can before we use them to do the longer climate simulations, which is phase 3, the future climate simulations. So here it's a similar idea of a couple of time slices, past and future, and doing analysis focused on the various climate hazards of interest to the stakeholders. And then the last phase will be actually working with the stakeholders to help them understand the data and how to use the data in ways that is actually most beneficial for them. So far, we've met with the stakeholders. We're in the process of developing the experiment protocol and the literature review of what's been done so far. And that's the island project. Lastly, I just want to mention a couple of other things. So there is a fair bit of work around kilometer scale model evaluation, emulation with AI. I mentioned it briefly already. We're looking at using that with the Pacific Islands work as well. And we're also working with state and federal governments to understand the climate-related risks using these kilometer scale projections. So there's several risks around things like wind gusts and hailstorms, which the low resolution models don't really give us any information on. And we're trying to understand better what information we're able to get from the kilometer scale models that is useful in these climate change risk assessment frameworks. And I'll finish there.
Thank you, Jason. Great talk and great work. So we have a couple of questions, okay, from the chat. The first question is, have you done any bias correction to the forcing data you used? And also related to that, have you seen any consistent bias in your 4-kilometer simulations?
So that's a really good question. So the first answer is we have done bias correction to the forcing data, but not for those NARCLIM 2.0 continuous 150-year simulations that I talked about. So they did not use bias correction. And do we see a consistent bias pattern? So you do end up seeing things like, and you might have noticed this when I show the results, in the north of the 4-kilometer domain in those simulations, it does tend to be a bit too wet. Now, that's the part of the domain where we get tropical influences. We get tropical systems coming in summer. And at 4 kilometers, it does seem to overdo the tropical system rainfall. Whereas in the south, you don't really see that problem very much, where we don't get those kind of systems. So there is some consistent bias patterns in there. And perhaps some bias correction beforehand would help reduce those, but we're yet to see if that's really true. Just talking about bias correction, I will just say that in particular for the Pacific work, the global models have a really consistent Western Pacific SST warm bias. And if we run our models directly with that warm bias into the models, it definitely means the rainfall simulation is worse. So we will definitely need to do some bias correction on that data before we do the long climate simulations in the Pacific work.
Okay, so do you use the WRF or WRF-Chem? I believe you use a WRF, right, to do your simulations.
Yes, we're using the WRF.
Yeah. Okay, so the questions are what how the aerosol impact is represented, okay, in the work.
Yeah, so we're using the aerosol-aware convection microphysics scheme from Thomson. And that's the key thing where the aerosols are impacting the simulation. I mean, the radiation is also aware, the radiation scheme is also aware of the aerosols. So it's got those two impacts that the aerosols are having. Now, it's not as sophisticated as you might be able to do with WRF-Chem, but we're not actually that interested in the chemical species and their reactions. We're interested in the aerosols and their impact on the hydrometeors. So I'm hopeful that we'll get something useful without going all the way to WRF-Chem.
Okay, so there are a lot of water, open ocean in your Pacific Island project simulation. So the question is, do you use the coupled ocean model?
So in what I talked about here, the first two phases, they're not with coupled ocean model. They're with prescribed SSTs, which is why I mentioned doing a bias correction of SSTs earlier. Now, I didn't talk about phase 3 of that project. That's a few years away, but that is a phase with coupled ocean models. So there's several groups experimenting with that right now, but mostly we're not ready to do a ocean-wide coupled regional scale simulations just yet.
Okay, thank you. Thank you again, Jason. And let's move on to the next speaker, Andreas Prein from ETH Zurich. And Andy is going to talk about understanding and projecting changes in extreme precipitation with kilometer-scale models. Go ahead, Andy.
Thank you, Faye. This is a really broad topic, so I decided to really break it up to 3 key messages that I wanted to convey today, which I think are really important. I'd also changed the slides a little bit to include the events that we experienced today in Hong Kong. Like, this is actually the satellite image that we have at the moment. You can see this very long rain band or cloud band stretching over thousands of kilometers, very stationary. This is what brought us this heavy rainfall today. So the 3 main messages that I wanted to convey today, and I think it fits to the previous talks already. The first one being really that if you have a well-calibrated kilometer-scale model, you can really reach observational quality when you go to extreme precipitation simulations. And I will show a couple of examples of that. Secondly, we can really use these models to learn more about how the future of heavy rainfall looks like. And here I will specifically talk about the scaling relationships between temperature and extreme precipitation, how to interpret those. I see those misused a lot in literature, and I think this is like really an important point where kilometer-scale models can help us to better understand how to interpret those relationships. And the third one is how extreme precipitations are really a multi-scale phenomena where different phenomena across scales are interacting to create the most heavy rainfall that we have. So starting off with the first point, how kilometer-scale models can get close to observational quality, I wanted to show these results. This is really the first kilometer-scale ensemble simulation that was ever performed over climate timescales. This is done within the Codex flagship pilot study over the Central European Alps. And what you can see here is basically on the left, observation, intensity of rainfall, frequency, and then heavy rainfall. It's the 99th percentile of hourly rainfall. And you can clearly see if you have a 12-kilometer model ensemble, your intensity is way too low. It's an order of magnitude too low, but also the extreme, the heavy rainfall is way too low, of course. But you compensate this error by a high frequency bias. And we saw this in other presentations today already. Once you go to 3 kilometers and you shut down the deep convection scheme, you can clearly see that we improve the frequency and intensity and heavy rainfall simulation in these models very systematically, and we can get very close to observational quality. And this is for a 10-year period that I'm showing you here. And this is, again, like this is a multi-model ensemble that we're looking at. So these are quite robust results. I think we can have a lot of confidence in those. But even if we look at even much heavier events, this is just an example. This is the West Virginia flood event. This is the daily accumulation during this event. This event was approximately 1 in 500 year event, caused a lot of fatalities and a lot of impact in the region in 2016. I show you 5 maps here. Precipitation accumulations go up to 200 millimeters, and I wanted you to guess, make a quick guess which one of those 5 plots is from observations and which one is from. This is actually a 3-kilometer WRF forecast that we're looking at here. The point really is that it's really hard to distinguish. The top left is the observations. The rest are 3-kilometer and 1-kilometer simulation. So that these simulations can reproduce the intensity, but also the spatial structure of those events very well. Although these events are so rare that we have never seen them basically in the development of these models, which is very encouraging. So basically just emphasizing that we can use these models for extreme rainfall assessments. We can look at a different example here. This is a tropical storm Bill, made landfall in June 2015 and caused very heavy rainfall over the southern states of the US. And this is actually a trick here because none of those maps is coming from simulations that are all observational data sets that we're looking at here. And this one at the bottom left is if you only use station observations, and you can immediately see if you only have stations, even if it's quite a dense station network, you cannot really confine the precipitation structure and precipitation intensities. Only if you include radar data, and this is what the other 3 do, you can get a more clearer picture of what the precipitation structure looked like during these extreme events. And even those disagree quite heavily on the intensity and spatial structure in some places. So there are really large observational uncertainties, even in regions where we have a lot of stations and radar data. Many other regions, Africa, for example, the observational uncertainties are much bigger. There's a big challenge for evaluating our kilometer scale models, but it's also meaning that because there are such large uncertainties in observations, the models are really able to get in this range of observational uncertainties if you calibrate them well. So moving on, looking at this scaling relationships between extreme rainfall and temperature. And this was, I think, the paper that kicked off this whole area of research in 28. Leonard and Maingard, what they showed here is a 100-year record of observed hourly precipitation, and they binned the hourly precipitation to daily temperature. And basically what you see here is, for example, 99.9 percentile of temperature at 6 degrees and 7 degrees. And if you connect these dots, you can see that precipitation intensity is increasing across the lower temperature ranges at 7% per degree Kelvin. This is basically what we expect from Clausius-Clapeyron relationship. But then above 10 degrees, they surprisingly saw that this increases to 14% per degree Kelvin. So this is, of course, very concerning because like nowadays, you can say at 22 degrees, they have 37 millimeters per hour. This is in Netherlands, quite heavy rainfall. But if we add 4 degrees, we might end up, if we have a 7% per degree Kelvin warming, we might end up at 50 millimeters. But if it's twice as high, we get up to 63 millimeters. So how these scaling rates refer to climate change is a really important question. So we plotted similar plots for the US, different regions in the US. And this is the Southeast, very different climate. It's more subtropical, also tropical cyclones are important there. And you can see across a large range of the spectra, we have this 7% per degree warming scaling. There's this hook at the top end. I will not talk about this. If you want to talk about this later, I'm happy to talk about it. But you can see that our 4-kilometer WRF simulation was able to capture this relationship extremely well. So this is current climate downscaling era interim at this time. So I want you to make a quick guess in your mind. Where do you think should this curve lie at the end of the century? So this is a 13-year WRF simulation that we performed. This is actually the future climate is a PGW, pseudo global warming simulation that we applied. And what you can see, this curve is not actually extended to higher temperature ranges, but the whole curve is shifted. So you can see it's basically a shift of the blue line to the top right. And this is even more obvious if you look at different climate region. This is now for California, which has a winter rainfall season, a very Mediterranean season. You can see it's actually a negative scaling relationship in this area. Warm temperatures, there's almost no rainfall in summer. But you can still see like the climate change signal is increasing. It's basically shifting the blue line across like parallel to the 7% per degree warming. So it's again an increase in extreme rainfall. So the point that I wanted to make here, the one thing that I really want you to take away, never do this. Never extrapolate from these curves into the future. It's really not an extrapolation. It's really the shift in these curves that determines future climate change. And don't use historic climate change scalings to project anything in the future, because you might end up in a region where we have negative scaling relationships, and certainly those regions doesn't mean this doesn't mean that we don't get extreme rainfalls that are higher in the future than the current climate. So last but not least, I wanted to also talk about the interactions of processes across scales and how they are important. I wanted to show this figure. It's a little bit busy, but it's very similar to what we experienced today. This was during the May season in this region of the world. We are somewhere down here, and you can see this cloud band similar to what we had today. And this was an extreme rainfall event in this area in 2015. And you can see how a different phenomena, like the top one, this is the jet stream being in the north of this cloud band. Then we have an atmospheric river that is set up to the south of it. And then we have mesoscale convective systems that develop within this cloud band. So all of these interactions together created an extreme event. And often in our analysis, we really look only at one phenomenon at one time. And we miss this interaction, which is really important. So therefore, we developed a tool which is called the Multi-Object Analysis for Atmospheric Phenomena tool, MOAP in short, where we can identify different phenomena across time and scale, connect those, and look at these interactions in more detail. So you can play with this tool online in the Google Colab notebook if you're interested. And we have 14 different phenomena that you can track: cyclones, anticyclones, mesoscale convective systems, tropical cyclones, and tropical waves, among others. So just to illustrate what we can do with this, if we, for example, look at the East Asian region, in this study, we picked the top 100 hourly extreme events from GPM iMerge in the period 2000 to 2020. And we looked at, for example, if you have an extreme event at this point, we looked at the radius of 1,000 kilometers, and we checked if there are any phenomena in this region. Like, for example, there could be a mid-level cyclone. The cyclone could have an MCS in the frontal area here. And there could be actually an anticyclone. So this is how you can build statistics on how extreme precipitation events are related to these different phenomena. And just to show you this for the IPCC regions, again, looking at the East Asian region, which is one of the most complex regions globally, actually, you can see that all of the extreme events that we had, this top 100 events, all of them were related to organized convection, so MCSs or tropical cyclones, which we also classify as MCSs. 90% of them had fronts, like this could be the Mayu front, but it could also be a front within a cyclone, for example. There were a lot of tropical wave activity that was related to extreme events in this region. This is actually the region which has the highest proportion of tropical cyclone-related extreme rainfall events globally. 50% of the 100 events were related to tropical cyclones, and actually a high proportion also from atmospheric rivers. So we can use this to better understand how extreme precipitation events form, but also to better quantify if your modeling system does produce extreme events because of the right reason. So coming back, these are the three takeaways that I wanted to convey. I also wanted to say, like, we're nowadays really able to do really large-scale simulations. This is just one example that we are performing nowadays at ETH with the ICON model at 2.5 kilometer global simulation for 4 years. This is the first 8 months of these simulations. You can clearly see this is the peak hourly rainfall from this 8-month simulations. You can clearly see the tropical cyclone tracks and their impact of extreme rainfall here. But you can also see all the MCS activities. So you see these lines in the central US, for example, in Argentina, but also in China, which are related to mesoscale convective systems that move along. And it's, of course, not only the rainfall that's impacting structures and environments, it's also other kinds of hazards, like, for example, high wind speed. And you can, for example, just look at the peak wind gusts, and you can clearly see how, again, tropical cyclones make their footprint, but also MCSs and derechoes and so on. So with that, I want to thank you for your attention, and I hope there is some time for questions. Thank you very much.
Thank you, Andy, for your excellent talk and very well, inspiring, okay, presentation. So we have time for questions. And there is a question, okay, from the chat. What metric did you use to track the surface cyclones? You use mean sea level pressure at the center or something else?
Yeah, exactly. Like it's an anomaly sea level pressure. So you track anomalous sea level pressure across time.
Okay. So another question is about this Clausius-Clapeyron relationship of plot. So why there is a scope at the higher temperature range?
So the main reason for that is if you have very high temperatures, you reduce rainfall because you go into a heat wave. So if you have very high temperatures, you often get very little precipitation. This is why you get this hook shape. So the atmosphere is getting quite dry and you cannot produce rainfall anymore. So you can accommodate that a little bit by using dew point temperature instead of air temperature, but often you still get this hook shape at the end of your scaling diagram. It's really this regime where you get quite dry air, where you cannot produce heavy rainfall anymore.
All right, thanks. Just a quick comment to Andy about your statement on the kilometer scale simulations will capture the precipitation, extreme precipitation. Okay, which I agree. But there are some constraints. I think the kilometer scale climate simulation was so successful because of the constraint by the ERF5, right? Reanalysis. And but in the forecast mode, particularly in the tropics, okay, it's very hard to still, I mean, increasing the resolution is not the whole answer, okay, to really increase the prediction of the extreme rainfall in tropical cities. We can continue that conversation, okay, tomorrow, I guess. I just want to make sure, okay, so I mean that there's some constraints, okay, to that statement.
I fully agree. Like I think I meant this well calibrated. This is part of that. Like in the tropics, we really have to invest in model development. Certainly, I fully agree with that.
Thank you. Let's move on to the next speaker. Yu Hongyun, okay, from Beijing Normal University. And she's going to talk about the kilometer scale multi-physics simulations of heavy precipitation events in northeast China.
Yeah, okay. Okay. Hello, everyone.
Hey.
Can you hear my voice?
Yes, loud and clear.
Thank you. Okay. Hello, everyone. I'm Hongyong Yu from Beijing Normal University, and I'm very happy to be here today to give a presentation. This is my topic today. Let me change my click. My topic today, and it's also the title of a paper. Firstly, I'd like to briefly introduce Northeast China. Northeast China is located in Northeast Asia, as it denoted by the figures in the red box here. And the figure in the lower left shows our specific study area. Northeast China has abundant soil use that is highly suitable for growing crops, making it a crucial grain-producing region in China. But in recent years, with global warming, extreme precipitation events have become increasingly frequent in this region. And here I gave some examples. And study heavy precipitation in Northeast China is challenging and can be specifically divided into 4 points. First, existing studies have pointed out there are complex multi-scale interaction processes in this region, and the heavy precipitation can be triggered by a variety of different types of weather conditions. And second, the precipitation mechanism in this region is different from that in southern China or in tropical regions. This region has less water vapor, and the strong low-level convergence often occurs during heavy precipitation. And because this region is located in the mid-high latitudes, the invasion of cold air can also cause atmospheric instability and trigger short-term heavy precipitation. And the third, the source of water vapor in this region are diverse. And the fourth, the terrain of the region region is a plain surrounded by mountains, and the compressed terrain has a notable impact on the precipitation process. And the kilometer-scale simulations have developed rapidly in recent years, and some studies have proposed some new ideas, which can be simply described as treating precipitation estimates from kilometer-scale simulation as a new source of information, perhaps in line with Andreas' first point before. And here are two examples I show here. One is using simulation to correct satellite precipitation products, and the other one is using simulation to supplement information on heavy precipitation events that lack observations. And currently, there are very few kilometer-scale simulation studies talking about Northeast China. And as pointed out in the previous WCRP report, there is a lack of kilometer-scale simulation studies targeting mid and high latitude phenomena. Therefore, we conduct kilometer-scale simulation research in Northeast China and hope to explore what new perspectives or conclusions kilometer-scale simulations can bring. This figure shows the domain of our WOLF model, which covers Northeast China and its surrounding areas. Our simulation used a grid spacing of 3 kilometers. We also use other data sets, including approximately 300 hourly stations observations and several common satellite precipitation products. EIA5 reanalysis is used to force the WOLF simulation. And we also compare EIA5 with WOLF data to understand the added value of dynamical downscaling. And here's our experimental design. For each case, each heavy precipitation event, we perform 24 simulations. Here we select several parameterization schemes that perform well based on existing literature. For the cumulus schemes, we have two options, enabling or disabling the scale-aware scheme. And we also include the 3 microphysics schemes and the 4 PBL schemes. In this study, we select 3 cases here. The first is a cold vortex case. Cold vortex, also known as a off-low. Much of the heavy precipitation in Northeast China stems from cold vortex. And the second is a typhoon case. In the summer of 2020, 3 consecutive typhoons affect Northeast China, causing widespread flooding. And the third is a heavy snowfall case, which occurred in early winter of 2020. And this figure shows the weather conditions in 3 different cases. The 3 rows represent 3 different cases. Simply put, the precipitation mechanisms in these 3 cases are different. So we can think of them as representing different precipitation mechanisms in this region. We first check the PDF of hourly precipitation. The reddish line represents the satellite precipitation products. The orange line represents the EIA5 reanalysis, and the black line represents the observations, the gauge observations, and the gray shading represents the spread of the kilometer-scale simulation example. We can select for case 1, the satellite precipitation product significantly underestimate the heavy precipitation. And overall, the example spread encompasses the observation curve, as it denotes here. And next, we check the temporal evolution of regional average precipitation. Here we discover an interesting phenomenon. When using station observation as a benchmark, the simulation with the largest deviation always approaches the observed curve better than the satellite precipitation product with the largest deviation. And we also evaluate the impact of different parameterization schemes using analysis of variances, the ANOVA. And overall, the microphysics schemes had the greatest impact on the extreme metrics. In this case, the maximum hourly precipitation. And the PBL scheme had the greatest impact on average metric. In this case, regional average accumulated precipitation. The scheme only had a significant impact on average accumulated precipitation in typhoon case, which is case 2. And we also check the vertical profiles of the hydrometeor in the 3 cases, the spread or uncertainties of the multi-physical examples, estimates of vertical profiles of the hydrometeor is similar to the uncertainty in the estimate of precipitation metrics. Case 1 shows the greatest variances. We can look at the gray shading. And case 3 shows the smallest variances. And we take a closer look at the cape and seeing at the representative moment in 3 cases, focusing on the y-axis here. And we find significant differences in convective instability among the 3 cases. The cold vortex case shows the greatest convective instabilities, resulting in the largest spread of the ensemble estimate precipitation metric, just like the slide it shows before. And also the snowfall case shows the least convective instability, resulting in the smallest spread of the ensemble estimated precipitation metrics. This shows that the convective characteristics of a case can notably influence the size of the difference in simulation for different physical configuration. And we also did an additional analysis. Here's what happened. Well, in our study, we use the method called the full metric approach. Which means that for a selective parameterization scheme, we consider all possible combination of different parameterization schemes. However, kilometer-scale simulation consumes a lot of computing resources, so this method is often not suitable for designing experiments. Another method is called sparse metrics, which means that only one scheme is modified at a time. Here I also give an example. Sparse metric saves computing resources, but it's easy to mix the physical configuration with performance. And the full metric consumes too much computing resources. So we wonder if there is a way to help the modeler find the best performing physical configuration with the least computing resource consumption. Due to time constraints, I won't go to details here. The general idea is that when you have a limited number of existing simulations, you use those simulations to estimate which physical configuration may perform best in the unrun simulations. And then add the corresponding simulation. And then continue adding simulations one by one, rather than randomly adding simulations. And in this figure, the black curve represents randomly adding simulations. The black curve. And the violet, red, yellow, and the green lines represent adding simulation using methods we described. We can see that the curve decreases more rapidly using this method, indicating that we can find a good physical configuration more quickly. And overall, this method can reduce computational resource consumption by approximately 50%. And I'd like to briefly share the latest progress of our research. We found that MCS appeared in all 3 cases, so we conduct further analysis. And in short, we select well-performing. Okay. In short, we select well-performing physical configurations and extend the simulation time to 1 year. We found that the kilometer-scale simulation tends to produce sharper MCS precipitation structure than satellite products. And furthermore, when combining satellite precipitation products where we analyze data to analyze the atmospheric environment of MCS. Physical inconsistencies can lead to notable problems. And well, we use several methods, and we think kilometer scale simulations can perform better than satellite precipitation products in estimating MCS associated precipitations. And due to time lift, I would leave out this part. And if you are really interested in our work, you can look at these papers. Okay, that's all.
Thank you very much, Hongyong. Thank you for your presentation. Good work. Due to the time constraint, I will just move to the next speaker. But for all the participants, you're welcome to interact, okay, with Yong tomorrow, okay, in person. Thank you. Let's move to the last speaker for our session, Leonard Wong.
Hi.
From Drainage Service Department. Oh boy, they have a tough
Hi.
job and challenge in the last 10 days. Okay.
It is.
So it is, right? Huge sympathy. But you protect us. Okay, thank you. So his talk is about the Mosaic model map application of extreme weather forecast in high resolution real-time flood risk visualization. Go ahead.
Yes, thank you, Faye. Good afternoon, everyone. Late modeling expert, ladies and gentlemen, it's my honor to be presenting here on behalf of the Drainage Service Department of the Hong Kong SAR government. To briefly introduce our department, we are actually the department, as Faye has just said, we are protecting the cities from the flood risk. We are to provide a world-class wastewater and stormwater drainage services to enabling the sustainable development of Hong Kong, driving the commitment to innovative flood risk management, of course. And some background, as you may have all aware, that Hong Kong is at a location on a tropical cyclone path, exposes us to storm surges that during high tides, elevated sea levels and threatening low-lying areas. Heavy rainfall during our wet seasons like today, coupled with the dense urban setting, amplifies our surface runoff, endangering large populations. And climate change intensifies these risks with more frequent and severe extreme weather, as we experience now. The frequent heavy rainstorm since last weekend is a good example. To address these challenges, the DSD, the Drainage Services Department, has adopted an integrated flood management strategy built on 3 pillars: adaptation, resilience, and management. We name them ARM for short. Adaptations means involving upgrading of infrastructure, such as stormwater storage tanks and storm tunnels, stormwater tunnels, drainage tunnels, to mitigate the flooding. Resilience employs temporary measures like the blue-green infrastructure to reduce runoff and enable rapid recovery. And management enhances emergency preparedness through our innovative technologies and real-time data dissemination. Essential to all these efforts is our commitment to hydrodynamic modeling, a cornerstone of stormwater drainage planning in Hong Kong. Hydraulic modeling in particular vital for identifying, planning, and designing adaptation measures, such as the storage tank and drainage tunnels, tailored for Hong Kong's diverse topography. Since the 1990s, our drainage master plan studies have developed models for catchments across our territory, from 1D river drainage models using Mike 11, advancing to the 1D, 2D model with structure measurement in Solback, and now utilizing the state-of-the-art 1D, 2D integrated catchment management models with InfoWorks ICM. These advancements enable precise simulation of urban and coastal flooding dynamics, and we are currently exploring AI too to further optimize our modeling efficiency, enhancing our predictive capabilities. However, despite these advancements, real-time flood risk management in Hong Kong faces significant challenges, as you may have imagined. Our highly urbanized and densely populated setting amplifies the flood impacts. A robust early warning system is crucial to minimize the damage, as demonstrated in recent typhoons and rainstorm events, where timely alert enabled resource deployment and saved lives and property. Contemporary rain and coastal flood risk requires a reliable and sophisticated hydraulic model that integrates precipitation, tide levels, and storm surges to capture Hong Kong's complex flood dynamics. Traditional modelings, while effective for planning, struggle with rapid catchment response in urban area where runoff can peak within minutes during the intense rainstorm. Prompt simulation result of weather forecasts are essential too to provide actionable insights for emergency response. Yet the traditional model runtimes are lengthy, often taking at least several hours, up to 10+ hours for a single catchment, not to say the whole territory. Due to a computational demands of 1D, 2D simulations, this delay is incompatible with the urgent need of a real-time flood risk management, making an innovative approach essential. To overcome these challenges, DSD developed the Mosaic model map with the 3M. We named them M-Cube, like the spinning cube there, a cutting-edge system delivering the real-time flood risk visualization. It has been successfully incorporated in our emergency response system. As demonstrated recently, the M-Cube's visualization provided great insight to teams to deploy our teams in areas with forecasted flooding risk, like typo in the tropical cyclone effect, ensuring timely protection and assisted resource deployment for speedy flood relief, such as directing the use of flood barriers, minimizing damages, and accelerating the recovery. M-Cube's excellence was also recognized at the recent Geneva Invention Exhibition in April this year, earning a gold medal with the congratulations of the jury. Before, let's move on to the technical details. Powered by the innovative mosaicing of hydraulic model results, rainfall nowcast, and the real-time hydrometric data, M-Cube delivers a flood risk map shown on a user-friendly web app interface, integrating real-time IoT data and meteorological forecasts. It shows a citywide combined effect of both rain-induced and tide-induced floods down to street level. This territory-wide visualization enhances emergency response against flooding and reduces flood loss, supporting the resilience and management pillars of our integrated flood management strategy. As highlighted, Hong Kong's flood risk and the limitation of traditional modeling necessitates innovative solutions like M-Cube. By leveraging the short-range warning of intense rainstorm in localized system, we normally call it this world's QPF, the quantitative precipitation forecast data set, with a high resolution of 500 meters spatial resolution and 6 minutes temporal resolution. M-Cube provides an actionable flood risk visualization across our city, aligning with DSD's commitment to advanced flood management. M-Cube strengthens resilience by enabling rapid deployment of temporary measures such as flood barriers in vulnerable area and ensuring the speedy recovery for management. Its visualization provides emergency control center with live flood risk trends and facilitating advanced planning and coordination with our frontline emergency control teams and enhancing Hong Kong's preparedness and response. So how does it work? It works in a 3-step methodology through model pre-run, scenario mapping, and mosaic compilation, which I'm showing each step by step. With our various rainfall and tide scenario over our 20+ catchments, we pre-run thousands of hydrodynamic situations using a robust 1D, 2D finite volume numerical flood model rooted in our drainage master plan studies, spanning from our 1990s. With decades of experience. Covering over the 20+ catchments, these models integrate the crucial information, including the drainage system, the networks, and the land use down to the street level details. Simulation spans diverse rainfall intensities and tidal levels, where flood extents store as GIS mosaic tiles for rapid access during the use. And in the next step is the scenario mapping. The M-Cube aligns the real-time forecast data with pre-run scenarios. The swell's QPF updates nowcast rainfall depths every 6 minutes. And we will aggregate these data for, say, the coming hour or the coming 2 hours. Overlay these QPF data on a catchment boundary and calculate the calculate the hourly rainfall nowcast at each point and analyze the rainfall statistics for these specific catchment. We also incorporate the predicted tide levels for the coming hour or the coming 2 hours from the Hong Kong Observatory's astronomical tide prediction, or alternatively, during the tropical cyclones effect, include the storm surge models. This integration enables MCube to select the most relevant flood risk map from the pre-run simulation database, matching the real-time condition and the 60, 90, and 120-minute forecast in advance for each of the catchments. For the last step is the Mosaic compilation. Using the GIS technique, MCube assembles selected tiles into the territory-wide flood maps, refreshing every 6 minutes. These citywide street level visualization, accessible through a web interface and exportable as GIS shape files, provides a territory-wide real-time flood risk model for decision making. And the development of MCube was targeted on over 4 objectives. And fortunately, these are all achieved. To be scalable, that the data product can be easily integrated into the real-time flood monitoring and alert system for emergency response planning. And it is easily upgraded with enhanced model result that we can further enrich our model database for a better result with time. And it is user-friendly. It has an intuitive user interface to share and track the citywide flood risk information up to a street level in a quick, effective manner. And on a web app interface, it can be shown to non-technical people within our office to share this information. And it is reliable. With the physical-based 1D, 2D model paired with the QPF data, we can ensure the dependable result that we have. And it is efficient, for it can go 24/7 with the pre-run simulation, which enable the rapid map generation and support the timely flood response. So MCube has transformed the Hong Kong flood management and directly supporting our integrated flood management strategy. It facilitates the Emergency Control Center to monitor live flood risk trends and allow advanced planning of emergency preparedness. During a recent typhoon, the Whipper, MCube's visualization guided the team to deploy flood barriers in areas like Taipo, ensuring timely protection. It also assists timely resource deployment for speedy flood relief, such as directing the pumping robots to inundated areas and minimizing the damage and accelerating the recovery. By providing real-time insight, MCube enhances coordination of emergency measures and strengthens Hong Kong's resilience. To conclude, MCube demonstrates how innovative mosaicing of hydraulic models, real-time IoT data, and meteorological forecasts creates practical flood management tools, strengthening the resilience and management pillar of our integrated flood management strategy. Flood risk visualization through MCube empowers proactive preparedness and rapid response, protecting Hong Kong community. We look forward to more advanced weather and climate modeling collaboration with all of you to further enhance these efforts to lead them to a higher level too. Originally, I prepared a video to show here, but I think from in terms of Zoom, it may not be showing too well. So for further interest, please feel free to take a picture of this QR code and visit the video later. Thank you.
Thank you, Nino. Excellent talk. There are a couple of questions. Okay, the first question is, can the MCube used by the public?
At the moment, it is for internal reference because there are some technical detail which is not so easily understood by the reader. So and it is still part of under a pilot scheme. So it is more left to testing stage. So it's for internal at the moment.
Very good, thank you. And also, next question is how can you probably elaborate a little bit more on how MCube will help with DSD's response to today's Black Rainstorm?
I think we have as you may be aware of, and is shown on the social media network, that we have a lot of work being done, and all the effort goes to our emergency teams. And we have our emergency control center, and MCube is part of them, that they can take a look at them. With the visualization of HAO's QPF, they have some insight of the future rainstorm and the potential potential flooding areas, that they can deploy the gangs in the vicinity of the sites, which provides advanced insight too, in addition to all the surface core or the core and the center for the case following up. In addition to these traditional methods, we have now some other ways of being more proactive to our work.
Thank you very much. Thank you. Let's thank you again for all the speakers and the engaging audience, okay, for the session. Thank you.
Hello, are we coming back now?
Do you hear me?
Yes, Xiaoming.
Yeah. Hello, everyone. So I'm Xiaoming. So I will be co-chair, and Professor Hui Su will be the chair of this session.
Oh, okay. Yeah, so thanks for coming back. So next we have three great talks. So we'll start with Dr. Marco Reale from Italy. So Marco, please take away.
Okay, I'm sharing my screen. Okay. Do you see my presentation?
It's coming up. Yes.
Yes. Okay, so good morning, good afternoon, everyone, and thank you for being here, and thank you for the convener to introducing me, to give me this opportunity to present my work. My name is Marco Reale. I'm a researcher at the National Institute of Oceanography and Applied Geophysics in Trieste. In this very short talk, I will introduce you a new modeling tool that we are currently using, my institute, that we developed in collaboration from our colleague from the International Center for Theoretical Physics in Trieste. This modeling tool was essentially developed to work on a specific area over the Mediterranean region, which is the Northern Adriatic region. The Northern Adriatic Sea region is essentially the red box that you see in the picture here. You can see for the picture is an area which is included in a region characterized by multiple environmental gradients. So just 50 kilometers, you can move from the sandy beaches to the mountains with the permanent snow coverage. The Adriatic Sea is a shallow basin which acts as a source of moisture in it for sometimes extreme convective precipitation events. It's also characterized by the presence of important coastal cities such as Venice, Trieste, and Ancona. It's also characterized by the presence of significant interaction. For example, the easterly Bora wind flowing over the Gulf of Trieste here essentially drives deeper water formation processes of the area, which drives the thermoline circulation of the Mediterranean Sea. Is also characterized by coastal flooding events, for example, the Acqua Alta events in Venice, and also is characterized by the presence of the Po River, which is on main freshwater source for the Mediterranean Sea. So if you want to simulate the climate dynamics of the area, you need to have a modeling tool which is able to take into account all the interaction among the different components of the climate system, but with at the same time an high level of details. Probably the best modeling tools that you can use is this guy here. This is REXCM-ES. This is a regional Earth system model, which is characterized by which uses an atmospheric model REXCM5, which is coupled with the surface length scheme, which is length 4.5, which has also an urban climate scheme, which has CLMU. Then we have the river model simulating the river discharge in the area, which is CHIM, and the model simulating the ocean dynamics, which is MIT GCM. Essentially, the run of each component is the exchange of forcing field, which is reported in green in the picture, and the interpolation of the forcing field on the grid of the receiving model is made by using a driver based on the Earth system modeling framework libraries. There are different versions of this coupled system with respect to previous version. This version that we use over the Northern Adriatic area as a new atmospheric module, REXCM5, which has a non-hydrostatic dynamical core, which can allow us to do convection-permitting simulation with much reducing computational cost. This model has been tested on different cortex domains that were also mentioned before by Jason, and shows significant improvement in the biases and statistical properties of precipitation and temperature. We have also a new routing scheme with CHIM that practically simulate dynamics of the river using a drainage network, which is built starting from a high resolution digital elevation model. it's possible to choose also the river that you can want to simulate the dynamics, just specifying a configurable drained area threshold. This is the domain of the H3 component of our modeling tool. So you can see the atmosphere with an horizontal resolution of 3 kilometers, which is convection permitting, and 41 zeta vertical levels. There you can see on the right panel the domain of the river model with approximately 1 kilometer of resolution, and finally on the bottom you can see the domain of the ocean model with the horizontal resolution of 700 kilometers, non-hydrostatic, and 59 zeta vertical level. We are currently running this model, and it's single component and offline mode in the evaluation run, which means in the era 5 period. So although we started the run from August 1st, 1987, and we consider a frequency of coupling between atmosphere and ocean of 3 hours, 1 day between atmosphere, ocean, and river. So initial boundary condition for the atmosphere, era 5. You can see here the time steps at 30 seconds. We are using aerosol from MERA. From the ocean, we use Copernicus analysis services for the physics with a time step of 50 seconds. Here I'm going to present the results for the first 13 years of run, which more or less we needed 1 month to do this one. This is just a simplified comparison between the standalone and coupled version of the same model. In this case, we are considering the river discharge model. On the left, we evaluate practically in this map. You can see different dots. Each dot is a station measuring the river flow. We compare the value measured with the value simulated by our model in the standalone and coupled version, and in the red box you see the coupling area acting during the coupling. So you can see that if you compare a standalone and coupled version just using these two metrics, which is the Killing-Cook efficiency and the simple biases, you can see that in the coupled version there is some improvements in the simulation of the river discharge. If you this is the same analysis that's been made for the 2 meters temperature, for example. On the left, you can see the average 2 meter temperature in summer according to Job's observation. In the central and right panel, you can see the simulated the biases between the simulated value and the observation. But looking at this way at the picture, you can see a significant. I mean, we are not able to see if there is if the coupling is an added value in improving the 2 meter simulation temperature. So we try to merge somehow biases and added value of the coupling. And practically on the left, again, you have the 2 meters temperature according to the observation. On the right, you have a map when with the contour line, there is essentially the mean biases between, I mean, in the two coupled system. We compare the two biases and we put on the maps just the minimum value, while the shaded color is essentially the difference between the absolute biases in the standalone system and in the coupled system, which means that if you have a positive value, this means that the biases in the standalone system is greater with respect to the biases observed in the coupled system. If you look at, for example, at the simulated temperature in winter, you can see that the coupling significantly improves the blue color, the simulation of the temperature along the coast in the Northern Adriatic area. I want to stress this is the area of where the coupling should be effective. We did the same analysis for the total precipitation, for example, so you can see that practically in winter, in the plain, there is still a dry biases and there is no significant improvements made by the coupling, while during the autumn, there is a significant improvements in the simulation of the total precipitation. The same happens, for example, in summer, while in spring, we have just some improvements on the western part of the basin. We have also improvements in autumn, for example, related to the precipitation regime, measured by the number of wet days. So you can see that the coupling significantly improve the simulated number of wet days in the plain area of the Northern Adriatic region. Here we compare, for example, the frequency of the precipitation events. We have in green and China the two different datasets, ERO for AM and YOBS, that are different datasets with different resolution. In the blue dot is the simulated daily precipitation events made by the coupled system, and the red are the simulated daily events, simulated events by the standalone system. So you can see that practically for extreme events, there is some improvements in our presentation of the extreme events. This is also more clear looking at, for example, the Earth 10 millimeters, which is the number of days with precipitation greater than 10 millimeters. Again, there is an improvement in representation of this kind of events in the plain during autumn, and the 20 millimeters events, again, over the plain area of the Northern Adriatic domain. Here, this is just a final example, another kind of analysis that's been made for the 99th percentile. So you can see that significant in some important areas, such as the area of Venice, there is an improvement in the simulated value of the 90th percentile simulated by the coupled system. So it looks like that the coupling improved the simulation of the precipitation related extreme in autumn in the coastal area of the Northern Adriatic region. So what we are doing now is currently investigating the source of these improvements. Maybe it's by chance, maybe it's most of transport, local circulation affected by the coupling. We are currently investigating the source of these changes. And what we are currently doing now is using this model to produce also signcast a kind of projection for the Northern Italian area. So thanks a lot for your attention.
Thank you, Marco. Yeah, we have time for questions.
Okay, I will ask a question. So Marco, thanks for the presentation. I just wonder why the ocean part needs a very high resolution. It seems that the resolution you used for ocean is quite very high.
Yeah, thank you for your question. Because our idea is to also characterize the surface circulation, the changes that can be somehow affected by the coupling. So the model is not only related to investigate, let's say, the changes in the atmosphere associated with the coupling, but also how the atmosphere can affect the simulation of the ocean dynamics with a very high resolution. Because essentially, the Adriatic region is, as I said at the very beginning, is an important site for deep water formation. So we can understand how much with this high resolution, with the coupling, how these water formation processes can be affected by the coupling itself.
Okay, I see. Okay, thank you.
Thank you very much for your question.
So with such high resolution, is the computation like time or concern if you want to real-time forecast?
Essentially, the coupled system, we are running on very powerful high performance computing cluster. And essentially, we are able to run in 24 hours, 6 months, just using a 760 processor. It's a computational heavy, let's say. But we are lucky since we have enough computational power so far.
Okay, that's great. So any other questions? Okay, so thank you, Marco. Then we'll move on to the next speaker. It will be Dr. Hiroki Kawase from Japan Meteorological Research Institute.
Can you hear me?
Yes, go ahead.
Thank you. So I'm Hiroki from Meteorological Research Institute. So many people talk about the heavy precipitation mainly in summer, but I will focus on the heavy snowfall in winter. So this morning we have a heavy rainfall in Hong Kong, but in Japan, the national record of maximum temperature has been broken, so 41.8 is observed. So the summer temperature is increasing, but in winter, we also have experienced heavy snowfall during cold air outbreaks. This is photos in winter. When cold air outbreaks occurs, the cold and the dry northwesterly blow from Siberia to Japan, and it obtains a lot of moisture from warm sea of Japan and creates a cloud slit like this. And it hits the Japanese mountain around here and causes heavy snowfall. These photos are taken in last winter, so you can see the cars in heavy snowfall and avalanches and so on. In addition to cold air outbreaks, the extratropical cyclones also causes short-term heavy snowfall in northern part of Japan last winter. So you can see the extratropical cyclone located around here and much moisture from southeast to this area. And this station, so Reale station, observed 124 centimeters snowfall, even in only 24 hours. It's a so heavy snowfall. I can't imagine this kind of heavy snowfall. So as you know, the global warming is accelerated recent years like this. And also around Japan, the SST is so high, about 3 to 5 Kelvin higher than normal. So our question is how historical global warming and high SST anomaly influenced the extreme snowfall occurred in last winter. To obtain the answers, our research group conducted event attribution studies. So there are two approaches. One is storyline event attributions, which uses negative pseudo-global warming approach. The other one is risk-based event attribution, which uses large ensemble global and regional climate simulations. So I conducted two methods, but I will focus on storyline approach first. So the regional model that I use is Japan Meteorological Agency non-hydrostatic model with 2 kilometer grid spacing. And we conducted 8 initial ensemble experiments and focused on early winter when cold outbreaks causes heavy snowfall. And we also focus on the specific event when heavy snowfall occurs in northern Japan. And this is control simulation. And we also conducted negative PZW experiments. Negative PZW means that so we eliminate the global warming component calculated by historical simulation, the difference between historical simulation and non-warming simulation. So we focus on the impact of historical global warming on the current extreme event. The other experiment is Kilometer-scale, which uses 10-year mean SST to eliminate the high SST anomaly around Japan. We also conducted Kilometer-SST non-warming experiments. So this is the result. So this figure shows the simulated 7 days total snowfall. You can see the large amount of snowfall over the coastal area around Japan here. And the other panel shows the difference between control simulation and the other sensitivity experiments. If we look at the global warming impact, the snowfall increases over the land here, but decreases over the ocean. On the other hand, high SST anomaly causes increase in snowfall not only over the land, but also over the oceans. We calculate the regional mean precipitation over the land in these rectangle regions. This table shows the changes. So you can see the global warming increased precipitation about 8.4%, and snowfall increased by 3.3%. But high SST anomaly increased precipitation about 19%, and snowfall increased by 17.8%. There are large differences. This difference is caused by the change in atmospheric structures. And this panel shows the potential temperature change across west to east. The global warming increased the potential temperature at the middle atmosphere about 5 hectopascal to 600 hectopascal. So this structure makes atmosphere more stable. But high SST anomaly increased the potential temperature at lower elevation because the heat source is around the surface. So this situation makes the atmosphere more unstable. So this results in the increases in large precipitation and large increase in snowfall. We also check the relative frequency of hourly precipitation and snowfall. You can see the control simulation show the high high intensity, like here among the other 4 experiments. This means the global warming and high SST anomaly enhances hourly precipitation intensity. But if we look at the hourly snowfall intensity is the highest in non-warming experiments. So this means the high SST anomaly without global warming is favorable for short-term heavy snowfall in Japan. So now the temperature is too high to cause the heavy snowfall. Next, we focus on the specific event in northern part of Japan. So this figure shows a 6-hourly total snowfall observed in Meteorological Research Institute, Japan Meteorological Agency. You can see the 6-hour total snowfall is over 50 centimeters. And this is the simulation result. The control simulation shows a similar horizontal distribution of snowfall, but the unit is different. This is water equivalent values. And global warming and high SST anomaly increased snowfall amount as with the previous result. And the high SST anomaly is larger than global warming impact. And we also check the atmospheric structure across here to here. So you can see the potential temperature is very low, so very cold air over the land like this. This is so-called cold air damming, when easterly wind flow over from the ocean to land. And if we check the impact of global warming and high ST on cold air damming, the global warming does not change cold air damming, although the potential temperature increases. But high SST anomaly changes the intensity of cold air damming. You can see the large increase in potential temperature over the oceans, but the increase the ocean, and you can see the summer contrast between ocean and land get larger. In these situations, the much moisture from the ocean rises over the cold dome around here and develops snow cloud around here, bringing extremely heavy snowfall over these regions. So we also checked the heavy impact of global warming on heavy snowfall using large ensemble experiments. In this method, we used global models, so atmospheric global model. The historical run is posed by observed SST in 2024 and 25 winter, while the non-warming experiments is forced by SSTs without historical warming. And we conducted 100 member ensemble simulations with 100 initial values. So we can obtain the 100 winter similar to 2025 and non-warming situation 100 winters. And we also conducted dynamical downscalings using 5-kilometer grid spacing regional climate model. Unfortunately, this is not the convection-permitting model. We use KF schemes, but high-resolution model. So we pick up the top 10 DJF maximum daily snowfall event occurred in Obhiro City near here. This is current warming condition, and this is non-warming condition. You can see the snowfall increase due to global warming as with the negative PGW method. And also, you can see the wind direction is also different between non-warming and current warming conditions. And this figure shows the SLP and the surface wind and temperature and pressed water vapor. In the warmer current condition like upper panels, the southerly changed to southeasterly, which is less warm than north southerly. This is because to keep the snowfall phases, because the temperature is higher than the industrial period. So this is very important for heavy snowfall because local dynamic change occurs due to global warming. Okay, this is our summary. We investigate the impacts of global warming and high SST anomaly on heavy snowfall in early February in Japan, using negative PGW and large ensemble experiments. We skipped to the result, but we are planning to the next strategy. So I will show the 5-kilometer ensemble experiments, but not convection permitting model. So we conducted additional dynamical downscalings using 2-kilometer or 1-kilometer convection permitting model from 5-kilometer large ensemble simulations. That's all. Thank you.
Thank you, Dr. Kwas. Questions?
Yeah, there is a question from Catherine asking, is there any reason why KF scheme is still turned on at the 5-kilometer resolution?
Thank you. So this is because when our research institute or Japan Meteorological Agency checked which one is better, turn on or turn off for the Japanese heavy, mainly rainfall, the result is turn on is better to reproduce the heavy snowfall if we use a 5-kilometer regional model.
Okay. Okay, thanks. Any other questions? Okay, I wonder, like in some of your figure, it seems that the so I wonder why if you look at the mountains, it seems that the downstream region get some reduction in rainfall. Is that the case? Yeah.
Which figure?
Like page 8. Oh.
Page 8? Here?
Yeah.
Here.
You're not showing.
Yeah, you're not.
Sorry.
Not sharing the slides.
I'm sorry. This here, right?
It's coming. Yeah. So yeah, like the surrounding region. Oh, it's maybe upstream, because the orange color you get some decrease as well. Yeah, I wonder why that's the decrease happens there.
So when we conducted similar experiments, so not only snowfall but also precipitation, in the downstream areas show the decrease in precipitation or snowfall. I think this is because this is a downward area and this is upward area. In the downward area, the downward flow may increase, may enhanced. The upward flow enhanced over the upward area, windward area. So enhanced rising and enhancement of downwind.
Okay, I see.
Yeah,
okay,
compensate. Okay, thank you, Dr. Kwas. We move on to the next speaker, Erin Doherty from NCAR. Okay, yeah, please take away.
You are muted, Erin.
Thank you. Can you hear me and see my screen?
Yes.
Okay, awesome. Let me go ahead and start this. Well, thanks everyone for sticking around through the end. I know it's been a long day on Zoom, so I'll try to keep everyone awake before we break for today. So I'm presenting some work I've done with Andreas Prein, along with Paulo Gorman, looking at changes to extreme rainfall over Puerto Rico in an ensemble of convection-permitting simulations. And so when we think of rainfall extremes over Puerto Rico, The first thing that might come to mind is Hurricane Maria in 2017. So this made landfall as a Category 4 hurricane. As you can see here, this made a direct hit on the island. You can see the eye centered right over the island. And it had 249 km/h winds and nearly 1,000 millimeters of rainfall. So here's just the rainfall map. It is in inches because it's from the US, but you can see that there's a bullseye over the southeast of the island, nearly 38 inches of rainfall, but most of the island saw pretty widespread high rainfall totals. And so obviously this caused a lot of damage to the region. So it resulted in nearly 3,000 deaths and $91 billion lost, making it the deadliest and costliest hurricane in Puerto Rico. Oops. And so in addition to rainfall extremes from tropical cyclones, Puerto Rico also experiences a number of different rainfall extremes. And so there's a nice study done in 2019 by Martinez et al., and they looked at the climatology of rainfall over the Caribbean. So this is showing just the seasonality of rainfall from both station observations in blue and then satellite data in orange. And we see this bimodal peak where there's a peak in the early season rainfall, so in May and June. And then we also see a peak in the late rainy season, which coincides with what we think of as hurricane season. And so there's a number of different large-scale controls relating to these different rainy seasons that we see in Puerto Rico. So this is a nice schematic showing all of these large-scale factors resulting in extreme precipitation in this region. And so we see in the early rainy season, this H is the North Atlantic subtropical high. So that starts expanding into the region. We see the Caribbean low-level jet plays a role here. And then we see the northward migration of the ITCZ. This all helps to produce convergence and uplift for rainfall during the early rainy season. During the late rainy season in September through November, we see that the North Atlantic subtropical high, that starts to contract on the western edge. We also see the Atlantic warm pool also contracts. And so this again creates convergence and produces the late rainy season or helps to enhance rainfall here. So a lot of the questions today that we've wanted to address is how will tropical precipitation change with global warming? And so a number of studies have done this in the past using GCMs mainly. And so this is one study by Brotons et al. In 2024. They looked at the wet season, so May through November, and they looked at the change in the mean precipitation. And so I drew, this is a red box over the Caribbean region, and they found that by the end of century, there will be a 20% decrease or 0.5 millimeter per day decrease in the mean rainfall in that Caribbean region. Another study actually looked at one metric of extreme rainfall. So they looked at the annual maximum precipitation, and they also found a decrease in rainfall within that Caribbean region of 3% per degree Kelvin of warming. And so these studies are suggesting perhaps there's a decrease in both mean and extreme rainfall over the Caribbean. And so we wanted to see, does that hold up in convection permitting models? So specifically, we are looking at how extreme daily precipitation over Puerto Rico changes in the early rainy season as well as the late rainy season by mid-century in convection permitting models. And so in order to do this, we use the MPAS atmosphere model, which is basically the replacement to the WRF model. What is nice about it and what we use in this case is we are actually running it globally. So everywhere outside of this outer ring here is at a 60-kilometer grid spacing. And then everything inside of this inner ring is actually a 3-kilometer grid spacing. So we have the convection permitting grid spacing over the area of interest, but we're letting everything freely evolve and run globally. For our forcing data, we use a 1/4 degree CSM high resolution data set called Mesoscale. I think that should be published soon. But basically, we can use this climate data for both the historical and future climate, and it's a 9-member ensemble that we're using from here. And so we use we identify the 99th percentile of extreme rainfall days during a historical and a future period. And since we are looking at daily extremes, we have 36-hour simulations with 12 hours for spinning up the model. And again, because it's convection permitting, we use the convection permitting suite that is available within MPAS. And so, as I said, we identified the top rainfall days. We identified these from the historical period in 2001 to 2021. We have 63 events here across the 9-member ensemble. And then the future, we identify 63 rainfall events from 2041 to 2061. We compare how these will change. And this is just to give you an idea of, what features are we simulating both globally and within the convection permitting grid. So hopefully this will play. This is just one of the extreme rainfall cases. So this was on September 5th and 6th of 2013. This is the outgoing long wave radiation. You can see the TC is right over Puerto Rico at this time, obviously producing a lot of extreme rainfall. But if I play this, you can see that we are, we're getting the ITCZ, which is really nice. You can see other bursts of convection globally, some frontal passages. And so this is a really nice tool to be able to zoom in the region you want to have high resolution, but then also simulate globally some of those other processes that could change in a future climate. And so you might ask, how good is our forcing data that we're using to simulate the extreme rainfall events? So we actually compared the CSM high resolution data, again, quarter degree, 6 hourly, against GPM iMerge in the thick black line here, and then also co-op stations. So these are just the ground truth of basically the rainfall we see over Puerto Rico. And that is shown by the gray line here. So this is a PDF of all the top 1% of rainfall days over the historical period from 2001 to 2021. Each of the 9 members that we use from the high resolution CSM data are shown by the different colored red and orange lines. And we can see that overall, the model data compares pretty well to what we see in the PDF distribution of rainfall extremes. It is interesting, though, that the different ensembles have this bifurcation where, some of them are showing something more in line with what we see in the co-op and iMerge data. And then the other ones are showing a much broader distribution and showing slightly higher rainfall extremes than what we see in observations. So we're capturing really a nice space here of the rainfall extremes within these different ensemble members. And so getting into the results, we looked at the change in the early rainy season on the top row and the late rainy season rainfall. The left column is showing the historical rainfall. The middle is showing the average of the future rainfall. And then the right column is showing that average future minus historical difference. So we see that the changes are pretty distinct among these different rainy seasons, where we see a 70% increase over this whole area in the early rainy season, and we see a 17% decrease over this area in the late rainy season. So very different changes here. So we wanted to understand, what are driving these differences that we're seeing, what storm types might be responsible for this. And so we actually used an MCS tracker to identify some of the storms. And this MCS tracker we're using is the tracking algorithm for mesoscale convective systems from Nunez-Ocasio and Moon 2024. And essentially it identifies MCSs by looking at the cloud top temperature. So it has to be less than 235 K, and that has to have embedded 219 cores. So pretty cold cloud temperatures. And it has to be at least 4,000 square kilometers. So this is a pretty large area over which to identify these MCSs. And then these are identified through polygons, which you can see here from a specific day. And the polygons have to overlap with a threshold of 0.5. And we say, okay, any MCS that meets all of these criteria and intersects with the island of Puerto Rico, that counts as an MCS impacting the extreme rainfall on that day. So we looked at the contribution of these storm types to the extreme rainfall in the early rainy season in green and the late rainy season in orange here. And now we're just looking specifically over the island of Puerto Rico. And as I mentioned, MCSs, you have to have at least 3 MCSs in day, or at least one that's greater than 3 hours duration, to make sure that these are sufficiently long-lived to contribute to the daily rainfall extremes. Isolated convection, those were identified where there were no MCSs or very short-lived MCSs. And then we identified tropical cyclones, which were pretty obvious to identify from a number of different model outputs. So overall, again, we see that increase in the early rainy season rainfall. Particularly, we see an increase is driven by the increase in rainfall from isolated convective storms over the region, and then also the MCSs. And then the late rainy season, we see a decrease in nearly all of the storm type rainfall, particularly from the isolated convective cells, and then somewhat from MCSs. I will note that we do see a slight increase in the tropical cyclone rainfall. So that's something we're looking into now, why that might be. But really, we wanted to understand why are we seeing this decrease in rainfall during that late rainy season. So to do this, we looked at changes in the relative humidity and the LCL height in the future in red, and then the historical climate in blue during the model initialization. And again, this is average over the island of Puerto Rico to give you an idea of the storm environment just over the island. And we see some pretty pronounced differences between the early rainy season and late rainy season, where in a future climate in the early rainy season, we see most of the profile, if not all of it, is showing pretty large moistening at all levels through the atmosphere. And we actually see the LCL heights are slightly lower in the future climate. So this all suggests more efficient rainfall production with more moisture and lower LCL heights. Whereas in the late rainy season, we don't see that much of a drastic increase in the relative humidity. And at mid-levels, we actually see a slight drying in a warmer climate and little change in, the LCL height there. So that could definitely impact some of the rainfall decreases we're seeing in the region. Finally, we looked at some of the changes in the large scale. So we looked at the mean sea level pressure shown in contours here, the 925 hectopascal winds shown by the arrows, and then the precipitable water in shading. So again, the top row is the early rainy season, the bottom row is the late rainy season, and then we have the change over here in the right-hand column. So both of these rainy seasons, we do see an increase in the moisture, but we do see a greater moistening within the early rainy season. It's a little bit hard to see, but the winds are converging a bit more over the island of Puerto Rico in the early rainy season, whereas we see slightly more of a diverging pattern in the wind in the late rainy season. So this is all suggesting that in the early rainy season, we're seeing more moisture convergence, more moisture increase, which is probably helping to fuel the greater increase in rainfall we see as opposed to the late rainy season. And so just to summarize, we simulated 63 historical extreme rainfall events and also 63 future extreme rainfall events over Puerto Rico at 3 kilometers by running MPAS globally in a current and future climate. So again, this is just summarizing, what we found, that we see this large increase is really in the early rainy season, and we see this decrease in the late rainy season, which we think is really tied to the changes in moisture, as well as, some of the convergence and divergence over the island. But we're still looking into how these large scale factors could play a role, such as changes in the North Atlantic subtropical high and the ITCC. So I think, that's all I have. So I'd be happy to take any questions. Thank you.
Thank you, Erin.
Yeah, we have a question from Lu Ling. He asks how the convection permitting suite do in the 60-kilometer region.
Yeah, that's a good question, Lulin. I haven't evaluated how well it's done at simulating things out, out in the 60-kilometer region, but I think that would be an interesting question to look into.
Okay. And Jason has another question. He said, you showed that some ensemble members had distributions that looked more like the observation and others are rather different. Do the future changes differ between those two groups?
Yeah, it's a great question, Jason. I haven't specifically looked into some of the individual ensemble members yet, but I think that could be a really nice way to separate out, maybe some of the more realistic ensemble members versus the ones that are fairly different. So one of the future things I want to look into is just the spread in the ensemble members within the future climate, just to see what does that rainfall variability look like in those different extremes. So yeah, great question.
Okay. Any other questions?
Yeah, I do have a question. So when you do the MCS tracking, so you have this inner domain of 3 kilometer, outer domain with 60 kilometer. Do you track like across this 60 plus 3 or just in the 3 kilometer?
We just track within the 3 kilometer domain just because it's going to be, better resolved. And we're really interested in the rainfall extremes over Puerto Rico specifically.
Okay, thank you.
Thanks.
Okay.
Go ahead, Shami.
Yeah, if no further questions, I wonder
There's another question.
there's another one. Oh, yeah, Na asks have you compared your results to the Mesoscale reference scheme in MPAS?
Yeah, that's a great question. I did play around with some of the different schemes. I think the convection-permitting scheme, from what I found, did the best job at simulating the rainfall extremes, but there were still cases where MPAS did not do a great job of capturing how extreme the rainfall was within this region. So I don't know if that's an issue with the model itself or it's an issue with fundamentally capturing some of the tropical precipitation extremes that we see generally. So I think that's really a question for further model development. But yeah, I think doing some comparison with different schemes would be a really nice study.
Okay.
Yeah. So we want to
Thanks.
thank all the speakers. That's for the talks. So any announcement? I think.
Yeah.
Shami.
Alexis, do you have any announcement? If not, I guess we will. So in the chat window, at 5 o'clock, there was a message about the gathering tonight. So there is a link for a Google form. So if you haven't signed up, but you will go, please sign up on the Google form in the chat window, and then you then see you this evening, in Crown Plaza. Okay, I guess. Yeah, I guess that's all for today. Thank you, everyone. Yeah.
Yeah, thank you.
Thank you.